Picture this, a massive stone castle under siege, its imposing walls battered by catapults and swarmed by invaders, slowly crumbling under the relentless assault. Now imagine, just beyond those crumbling stones, a fortress made of wood towering, resilient, and utterly unyielding. While history books have long celebrated the might of stone fortifications, they've quietly ignored one of the most astonishing secrets of medieval engineering: wooden fortresses that not only survived where stone failed, but often outperformed them in the most brutal conditions imaginable. These were not primitive palisades or temporary shelters. They were sophisticated, brilliantly designed strongholds crafted from timber, earth, and pure ingenuity structures that defied the expectations of their enemies, and perhaps even more surprisingly, the narratives written by later generations. What if everything we thought we knew about ancient defense was incomplete? For centuries, the story of fortresses has been dominated by images of imposing stone castles, symbols of power, permanence, and technological achievement. But hidden in the shadows of these celebrated monuments lies a richer, more dynamic truth: that some of history's most resilient defenses were built not from rock, but from wood. From the misty forests of Eastern Europe to the earthquake-prone mountains of Japan, master builders used locally sourced timber to create fortresses that could flex under impact, adapt to threats, and repel invasions that left stone walls in rubble. These wooden marvels were faster to build, more cost-effective, and in many cases more strategically versatile than their stone counterparts. Yet their stories have been largely forgotten, overshadowed by the grandeur and perceived superiority of masonry. Today, we're setting out on a journey to rediscover these overlooked triumphs of engineering, to walk the ramparts of history's great wooden fortresses and uncover the principles that made them so astonishingly effective. We'll explore how Slavic gords withstood nomadic hordes, how Viking ring fortresses mastered Scandinavian winters, and how Japanese Yamashiro castles danced through earthquakes that would have shattered stone. Along the way, we'll meet the defenders who trusted their lives to timber, the builders who turned simple trees into near-impenetrable defenses, and the cultures that leveraged their environment not as a limitation, but as a source of strength. This is more than a history lesson. It's an invitation to see the past with new eyes, to challenge assumptions about strength and innovation, and to discover how lessons carved in wood centuries ago might just hold the key to building a more resilient and sustainable future. So settle in, open your mind, and join us as we step into a world where humble materials achieved legendary results. Long before the age of grand stone castles, the landscape of defense was defined by wood. In the vast, untamed forests of Europe and the resource-rich river valleys of Asia, communities turned to the most abundant material they had: timber. This wasn't a choice born of primitive limitation, but one of brilliant practicality. Imagine a threat emerging on the horizon: a rival tribe, a raiding party, a migrating horde. A society relying on stone would need years, even decades, to quarry, transport, and assemble a defensive stronghold. But a community skilled in woodcraft could erect a formidable fortress in a matter of months, sometimes even weeks. This incredible speed of construction was their greatest strategic advantage, allowing for a rapid response to immediate dangers that stone could never hope to match. These early wooden fortifications were far more than simple stockades or fences. They were sophisticated, multi-layered defensive systems that showcased a deep understanding of engineering and tactics. A typical fortress might feature a series of concentric wooden walls, each one higher than the last, creating a deadly killing zone for any attacker who breached the outer perimeter. The gatehouses were not mere openings but intricate choke points, often designed as narrow, winding passages that could be sealed with massive timber doors and then rained upon with projectiles from elevated platforms above. Beyond the walls, builders integrated the natural landscape into their designs, digging deep, water-filled moats that isolated the fortress and making clever use of steep hillsides or river bends to limit the angles of attack. We see this ingenuity echoed across disparate cultures, each adapting the principles of wooden fortification to their unique environment and challenges. The Slavic peoples of Eastern Europe constructed their gords, formidable strongholds that served as both military bastions and thriving community centers. In Scandinavia, the Vikings mastered the use of timber, not just for their legendary longships but for their fortified settlements and trading hubs. Meanwhile, in ancient China, during the Warring States period, wooden watchtowers and frontier walls provided flexible, rapidly deployable defenses long before the stone versions of the Great Wall were ever conceived. This global pattern of innovation wasn't a coincidence. It was a universal solution to a universal problem, proving that effective defense relies more on intelligent design than on the hardness of the materials used. It might seem counterintuitive at first. How could a material that burns and rots possibly stand up to the immense, crushing force of a siege? Yet, when we examine the physics and the practical realities of medieval warfare, wood's hidden advantages become startlingly clear. Think of it like this: a stone wall is rigid and unyielding. When a massive catapult stone slams into it, that energy has nowhere to go. The force transmits directly through the masonry, creating shock waves that spiderweb through the stone, splintering mortar and causing catastrophic, irreparable cracks. It's a single, devastating event. Now, imagine that same projectile striking a thick, green timbered wall. The wood doesn't just resist, it reacts. It absorbs the blow, compressing and flexing like a giant spring. The energy is dissipated along the entire structure, often leaving little more than a deep, splintered dent. This wasn't a weakness, it was a built-in shock absorption system. Defenders could actually watch a wall shudder and then settle back into place, a sight that must have been as demoralizing for the attackers as it was heartening for those inside. This critical difference was magnified by environmental factors that stonemasons simply couldn't overcome. In the frigid winters of Eastern Europe and Scandinavia, the moisture trapped within mortar would freeze and expand, slowly but surely prizing stones apart from within. A stone castle left untended over a harsh winter could enter the spring campaigning season structurally compromised before a single enemy even arrived. Wood, especially when properly treated and maintained, was far less susceptible to this kind of insidious decay from the elements. But the most significant tactical advantage, often overlooked, was the sheer speed of repair. During a prolonged siege, a breach in a stone wall was often a death sentence. Repairing it under a hail of arrows was nearly impossible, requiring skilled masons and time that defenders simply did not have. A wooden fortress, however, could be patched and reinforced with astonishing speed. If a section of wall was battered, defenders could simply bolt on a new prefabricated panel of heavy timber overnight, or stack earth-filled baskets behind the breach to create a temporary but effective bulwark. This ability to heal itself during battle made a wooden fortress feel almost alive to its besiegers, a frustrating, regenerating obstacle that could negate weeks of bombardment in a matter of hours. We see this play out starkly in the historical record, particularly during the Mongol invasions of the 13th century. As their armies swept westward, they frequently encountered both stone castles and formidable wooden fortresses known as gords. Time and again, chroniclers noted that the stone strongholds, for all their imposing grandeur, often fell more quickly. Their rigid walls would succumb to concentrated battery from siege engines, and once a section collapsed, the defense crumbled. Yet the wooden gourds, with their interlocked timber frames and earthen embankments, proved incredibly resilient. They could withstand the bombardment, and their flexible nature allowed defenders to constantly adapt, shoring up weak points and countering Mongol strategies in real time. As military historian John France has pointed out, this versatility granted defenders a psychological edge as well. They weren't just trapped in a static tomb waiting for it to break. They were active participants in the defense of their own walls, able to respond, adapt, and ultimately endure in a way that those behind stone simply could not. This wasn't a primitive stopgap. It was a sophisticated and often superior approach to defense, setting the stage for the incredible engineering we find in specific fortresses across the globe. To truly grasp the genius of these structures, we need to step inside one of these Slavic gords. Picture not just a wall, but an entire engineered landscape. The first challenge for any attacker was simply getting close. Encircling the entire settlement was a vast, deep ditch, often flooded with water diverted from a nearby river. Behind that, a steep, sloping earth rampart rose up, its sides reinforced with woven wicker or timber lattices to prevent erosion. And then, crowning this man-made mountain, stood the main event, the wooden wall itself. But this was no simple fence. It was a multi-layered masterpiece of carpentry constructed from massive, vertically set logs, oak or pine, often left with their bark on for added toughness. These logs were interlocked at the top by a continuous horizontal beam, creating a solid, continuous rampart that could be walked along by defenders. At regular intervals, tall watchtowers jutted out, providing overlapping fields of fire for archers. The main gate was a fortress in its own right, a complex, narrow passageway that funneled attackers into a death trap where they could be assailed from above and from the sides simultaneously. The true secret to the Gourds' resilience, however, lay in its brilliant fusion of materials, a composite structure far ahead of its time. The wooden wall was not freestanding. It was backed by the immense weight and stability of the earthen rampart. This combination was devastatingly effective. The earthwork absorbed the immense kinetic energy of projectiles, stopping them dead, while the wooden facade prevented the erosion and weathering that would have slowly degraded a bare earth wall. This design created a defensive system that was both incredibly robust and surprisingly flexible. When a battering ram struck, the logs might shudder and splinter, but the packed earth behind them would not yield. Even if an attacker managed to set a section of the wall on fire, the earth core would act as a firebreak, often limiting the damage to a single, repairable panel, rather than allowing flames to race along the entire perimeter. Nowhere is this sophisticated engineering more vividly preserved than at Biskupin, in modern-day Poland. This spectacularly well-preserved site, dating back over 2,500 years, offers a frozen-in-time glimpse into the Iron Age precursor to the medieval Gourds. Excavations reveal a densely packed settlement on a marshy peninsula, its defenses a perfect example of this wood-earth synergy. The builders drove thousands of sharpened piles into the boggy ground to create a stable foundation. Upon this, they erected a colossal box-like rampart filled with sand, stones, and earth, all held in place by an intricate cage of timber beams. The joinery is what truly astonishes archaeologists. They used complex locking joints, not just simple notches, to connect horizontal and vertical members. This framework was designed to move and settle as a single, unified structure, allowing it to withstand ground shifts, freeze-thaw cycles, and the tremendous impacts of siege warfare without collapsing. Walking the reconstructed sections today, you can almost feel the walls breathe, a living, flexible barrier that was far more intelligent than a static pile of stone. This architectural brilliance translated directly into legendary defensive successes against some of history's most fearsome warriors. The Magyars, a confederation of nomadic horsemen who terrorized Europe in the 9th and 10th centuries, were masters of lightning-fast raids. They could sweep across the open plains, overwhelming unprepared villages and outrunning slower feudal armies, but they consistently found themselves stymied by the Gourds. Their preferred tactics, swift cavalry charges and hails of arrows, were useless against these wooden citadels. The deep ditches stopped their horses cold, and their arrows thudded harmlessly into the thick timber and earth. Forced into the unfamiliar and grueling role of besiegers, the nomadic warriors lacked the heavy equipment and patience required to break these defenses. Chroniclers of the time recorded their frustration, noting how Slavic communities, warned by signal fires from one gorge to another, would funnel inside with their livestock and supplies, then watch safely from the walls as the invaders wore themselves out against the impregnable defenses. The Gord was more than a fortress. It was the heart of Slavic resistance, a symbol of communal strength that allowed a settled people to endure and ultimately prevail against the relentless tide of the steppe. While the Slavic Gourds demonstrated a brilliant fusion of earth and timber, a different kind of wooden marvel was taking shape further north, one that traded organic, sprawling designs for breathtaking geometric precision. Imagine a structure so perfectly circular that its curving wooden ramparts seem to defy the very nature of construction with organic materials. This was the Viking ring fortress, and sites like Trelleborg in Denmark stand as a testament to a level of planning and standardization that feels almost modern in its execution. Built during the 10th century under the reign of King Harald Bluetooth, these fortresses were not haphazard strongholds. They were masterpieces of prefabricated military architecture, designed to project royal power and control key territories with overwhelming efficiency. The sheer scale of their symmetry suggests the work of a single, brilliant master builder or a tightly controlled royal directive, imposing order on the landscape with mathematical certainty. The construction of a ring fortress was a colossal undertaking that began not with digging, but with meticulous surveying. Using simple but effective tools like measuring poles and ropes, Viking engineers would lay out two perfect concentric circles to define the inner rampart and the outer ditch. The inner circle, which could be up to 150 meters in diameter, was then divided into 4 perfectly equal quadrants by 2 main roads that intersected at a right angle at the exact center of the fortress. Within each of these 4 slices, 4 nearly identical longhouses were constructed in a square formation, all facing the central courtyard. This wasn't just aesthetic, it was a logistical revolution. Every component, from the massive oak beams forming the longhouse walls to the specially cut planks for the rampart walkway, was designed to be interchangeable. This meant that construction crews, possibly even pre-trained work gangs, could erect these formidable complexes with astonishing speed, perhaps in a single season, allowing a king to suddenly plant an unshakable bastion of authority in a restless region. The fortress wall itself was a defensive innovation. Unlike the earth-backed ramparts of the Gourds, the Trelleborg-type rampart was a freestanding wooden bulwark. It was constructed using a technique known as skip raid, where massive, radially arranged oak beams formed an inner and outer wall. The space between these 2 timber faces was then packed with earth and stones, creating a formidable barrier that was thick at the base and tapered towards the top, where a protected fighting platform allowed defenders to command the entire perimeter. The gates, positioned at the 4 cardinal points, were engineering puzzles in themselves. They were built as narrow, tunnel-like passages through the thick rampart, forcing any attacker to enter in single file, completely exposed to defenders on the platforms above. This design eliminated the vulnerable flanking that often plagued square or rectangular fortifications, ensuring there was no blind spot for an besieging army to exploit. Esteemed historians like Else Rosedal have long argued that the true genius of these ring fortresses lay not just in their defense, but in their function as integrated military and administrative hubs. They were not isolated forts but central nodes in a network of control. The 4 longhouses in each quadrant could garrison a significant number of the king's professional warriors, his herd, but they also served as workshops, storerooms, and barracks. The precise internal layout allowed for rapid muster and deployment of forces. A commander in the central plaza could direct troops to any of the 4 gates within moments. Furthermore, their placement was strategic, often located near navigable rivers or ancient roads, allowing them to control trade, collect taxes, and serve as a secure base for royal officials to administer the surrounding land. They were instruments of consolidation, tangible symbols of a king's ability to organize, build, and command on a grand scale. Perhaps the most compelling evidence for their sophistication is their durability against the elements. The harsh Scandinavian climate, with its freeze-thaw cycles, driving rain, and strong winds, is notoriously brutal on architecture. Stone structures, unless meticulously maintained, can suffer from frost damage and mortar decay. But the Vikings built with a deep understanding of their material. The massive oak timbers, often charred or tarred at the bases set into the ground, resisted rot and insect infestation for generations. The circular design was also inherently stable, distributing stress evenly and offering less wind resistance than angular buildings. This resilience is why, despite being abandoned and plowed over for centuries, the ghostly outlines of these fortresses remained imprinted on the Danish soil, waiting for archaeologists to rediscover them and reveal their perfect geometry to a modern world that had long forgotten the Viking talent for monumental wooden architecture. Across the world, in the volcanic islands of feudal Japan, a completely different set of environmental pressures gave rise to another pinnacle of wooden engineering, the Yamashiro or mountain castle. Here, the primary enemy wasn't the nomadic horseman or the freezing winter, but the very ground itself. Japan sits atop the violently shifting Pacific Ring of Fire, a land perpetually trembling with the threat of catastrophic earthquakes. For Japanese architects, building for permanence meant building for flexibility. A rigid stone tower so prized in Europe would be a death trap. Instead, they looked to the forests covering the mountainous terrain and developed an architectural philosophy where wood wasn't just a material, it was a dynamic partner in a dance with the elements. The Yamashiro was designed not to resist force but to absorb it, move with it, and ultimately survive it. The most visually stunning example of this principle is the iconic Tenshu or castle keep. From the outside, structures like the magnificent Matsumoto Castle present a formidable, multi-tiered silhouette of sweeping roofs and white plaster. But their true genius is hidden within the walls. The core of the castle is a massive central pillar, often a single, enormous tree trunk known as the Shinbashira. This pillar does not rigidly support the weight of the entire structure like a Greek column. Instead, it acts as a giant pivot point, a central axis around which the rest of the flexible wooden framework can sway and oscillate during a tremor. The floors are built as independent boxes stacked around this central pillar, connected by complex joinery that allows them to shift and slide against each other. In an earthquake, the entire castle is designed to rock and shudder like a ship on a wave, dissipating the seismic energy harmlessly through its joints and flexing beams, a phenomenon engineers now call structural damping. This incredible flexibility was achieved through joinery techniques so advanced they border on artistry. The shin-zukuri method, meaning heart construction, involved carving intricate, interlocking joints that transferred weight and stress without a single metal nail. Craftsmen would shape tenons and mortises with such precision that the wood would grip itself, creating a structure that was both incredibly strong and capable of minute movement. These joints acted like shock absorbers, allowing beams to flex and then snap back into place. This was a stark contrast to the iron cramps and molten lead used to secure stone blocks in European castles, which would simply shatter under the same lateral forces. The Japanese approach understood that to be truly strong, a building first had to know how to yield. But the Yamashiro's defenses were not solely designed for tectonic plates. They were also masterclasses in military deception and psychological warfare. Perched high on steep mountainsides, the approach to a castle like Heimji, the famous White Heron Castle, was a carefully orchestrated gauntlet of confusion. Attackers would be funneled through a labyrinthine series of winding paths, dead ends, and heavily fortified gates, all while being exposed to arrow fire from multiple hidden angles. These paths were designed to strip away any momentum, break up formations, and disorient the enemy completely. Trapdoors, false walls, and concealed sally ports allowed defenders to appear, strike, and vanish seemingly at will. For a samurai army expecting a straightforward assault on a static wall, attacking a Yamashiro was a nightmare of uncertainty, where the castle itself felt like a living, thinking adversary. The chronicles of the Sengoku period, the era of warring states, are filled with accounts that testify to the effectiveness of these wooden fortresses. They withstood long sieges, repelled direct assaults, and served as the impregnable hearts of powerful clans for generations. Their success was a direct result of a design philosophy perfectly harmonized with its environment. The need to withstand earthquakes dictated a flexible wooden frame, and that very flexibility then provided unparalleled advantages in repelling human invaders. It's a powerful demonstration of a universal truth we've seen from the Slavic forests to the Scandinavian plains. The most resilient structures aren't those made from the strongest materials, but those whose design most intelligently responds to the world around them. The Yamashiro stands as a timeless lesson in bending so you do not break. This intimate relationship between fortress and landscape wasn't just a matter of convenience. It was the very soul of their design philosophy. Builders didn't force a single, rigid blueprint onto the world instead. They became masterful interpreters of their environment, reading the local topography, climate, and available resources like a blueprint provided by nature itself. In the endless, dense taiga forests of Scandinavia and Eastern Europe, timber wasn't just abundant. It was the defining characteristic of the landscape. This overwhelming abundance meant that constructing a fortress was a matter of organization and labor, not a generations-long quest for rare materials. A community could fell, shape, and raise the walls of a formidable gourd using the trees from the very land it was meant to defend, creating a structure that was literally woven into the fabric of its surroundings. This local sourcing created an incredibly efficient logistical loop, turning a potential obstacle, a dense forest, into the primary building block of security. Conversely, in the volatile, earthquake-prone islands of Japan, the environment presented a completely different set of challenges. Here, the ground itself could become a lethal enemy. A rigid, brittle stone tower, so prized in stable European kingdoms, would be a death trap during the violent tremors that regularly shook the region. Japanese architects, through centuries of observation and innovation, understood that survival demanded flexibility. This fundamental need gave rise to the astonishing wooden frameworks of the Yamashiro, designed to sway and shudder with seismic energy rather than resist it unto destruction. The choice of wood was therefore not a compromise but a direct and brilliant response to a geological reality. The towering stone keeps of Europe would have crumbled into tombs under the same forces that the flexible wooden tenshu of Matsumoto Castle could simply ride out, emerging shaken but standing. Beyond forests and fault lines, other extreme environments demanded even more specialized adaptations. In the vast, waterlogged Pripyat marshes of Eastern Europe, stable ground was a myth. Here, builders turned to a technique still used in waterfront communities today, piling. They drove long, sharpened timber posts deep through the unstable peat and muck until they hit a more solid substrate beneath. Upon this stable, man-made forest of pilings, they then constructed their wooden fortresses. This elevated foundation created a stable, dry platform in the heart of a treacherous swamp, a defensive advantage that was almost insurmountable. An army attempting to besiege such a fortress would find itself bogged down literally and figuratively, struggling through impassable terrain while defenders looked on, safe and dry. Stone construction in such an environment would have been a folly. The immense weight of masonry would have caused the entire structure to sink inexorably into the soft ground, a lesson learned the hard way by many overconfident builders throughout history. Even in arid climates where we might assume wood would be vulnerable to rot and desiccation, it often held surprising advantages over stone. In regions with low humidity and infrequent rain, the mortar used to hold stone blocks together could fail. Without moisture to maintain its chemical integrity, the mortar could crumble to dust, turning a solid wall into an unstable pile of rocks waiting to be pushed over. Treated wood, however, could thrive. Ancient builders developed sophisticated methods of preservation, charring the surfaces of posts to create a hardened, insect-resistant crust, or soaking timbers in tar, oil, or brine to prevent decay. In these dry conditions, a well-treated wooden post could stand for centuries, maintaining its structural integrity long after the mortar in a nearby stone structure had turned to powder. This adaptability across such a wildly diverse range of environments is a key reason why wooden fortifications were a truly global phenomenon. As landscape archaeologist Oliver Creighton has often emphasized, these structures were not imposed upon the landscape but grew out of it. This harmonious relationship made them not only practical but often tactically superior to more advanced stonework in their specific ecological niches. A stone castle in a swamp is a sinking ruin. A stone castle in a seismic zone is a collective grave, but a wooden fortress designed in conversation with its environment leveraged those same challenges into defensive strength. This profound understanding that the best defense works with nature rather than against it paved the way for the even more intricate secrets hidden in the joints and beams of these structures, secrets that turned simple timber into seemingly impossible feats of engineering. If stone castles were the blunt instruments of medieval warfare, relying on sheer mass and immovability, then wooden fortresses were the precision scalpels. Their true strength wasn't in the timber itself, but in the nearly invisible spaces between the beams, the intricate, masterfully carved joints that connected everything. This is where the real engineering genius resided, in the hands of carpenters who understood wood not as a static building block, but as a living, breathing material that needed to move. They weren't just building walls, they were assembling giant, three-dimensional puzzles designed to sway, shudder, and settle as a single, unified organism under stress. Consider the humble log cabin corner. You might picture a simple overlap of two notched logs. That basic technique, known as saddle notching, was just the starting point. For a defensive wall that had to withstand the impact of a multi-ton battering ram, much more was required. Slavic builders perfected a method called blockbow, where each massive log was meticulously carved with a deep, interlocking notch at its end. When assembled, these logs locked together so tightly that the weight of the entire wall above helped to seal the joint tighter under pressure, much like clasping your hands together. This created a structure with immense inherent strength, but crucially, it also allowed for a minute degree of movement. When a projectile struck, the shockwave didn't stop dead. It traveled along the wall, dissipating its energy through a chain of these flexible connections. The wall would groan and shift, but it wouldn't snap. The Vikings, however, took this concept of flexible strength to a breathtaking level of geometric precision. Their ring fortresses relied on a technique known as Laftewerk, which used meticulously squared timbers rather than round logs. The corners of these structures were masterclasses in joinery, often employing a method called the double dovetail joint. Imagine the end of a horizontal beam carved into a distinctive, flared shape resembling a dove's tail. This would then slot perfectly into a negative space of the exact same shape carved into a vertical upright. The genius of this design is that it resists being pulled apart from every direction. It's a locking mechanism that transfers weight and stress with incredible efficiency, creating a corner that is both immensely strong and capable of flexing. To further reinforce these critical junctures, they added diagonal braces, creating internal triangles, the most stable geometric shape known in engineering, to distribute any concentrated force evenly throughout the entire framework. This wasn't just theory. We have stunning, preserved evidence of this mastery in a slightly different context: the Oseberg ship burial. The majestic Viking longship, discovered in a clay mound in Norway, is a testament to the same construction principles used in their fortresses. Its hull isn't nailed together. It's stitched with overlapping planks fastened with supple root lashings and complex joints. This allowed the entire ship to be incredibly flexible, riding over ocean waves like a sea serpent rather than fighting them as a rigid vessel would. A fortress wall built with the same philosophy would behave similarly under the waves of a siege assault, bending instead of breaking. The tools to achieve this were surprisingly simple but required immense skill: the broadaxe for rough shaping, the adze for fine smoothing, and the auger for boring precise peg holes. The final component was the wooden peg or tree nail, which was pounded into soaked holes. As the peg dried and expanded, it would clamp the joint together with a vice-like grip far stronger than any iron nail, which would simply rust and loosen over time. The true battlefield advantage of all this intricate joinery was repairability. Imagine a section of a stone wall shattered by a catapult. Repairing it under fire was a nightmare, requiring skilled masons to hoist and set heavy new blocks while dodging arrows. Now imagine that same breach in a wooden wall built with modular joints. The damaged section, perhaps a single panel of interlocking beams, could often be identified and detached. Using pre-prepared replacement units stored inside the fortress, a work crew could literally slot a new panel into place overnight, using wooden mallets and levers. By dawn, the wall could be made whole again, a demoralizing sight for any besieging army that had spent weeks achieving that single breach. This was the ultimate expression of the carpenter's art, turning a fortress from a static monument into a resilient, adaptable, and almost living entity that could heal its own wounds under the most desperate circumstances. Yet for all their physical resilience, the true mastery of these wooden fortresses often unfolded not on the battlefield, but in the minds of those who sought to conquer them. A stone castle announced its strength with cold, silent immensity, a challenge of pure physics, but a wooden fortress engaged in a far more subtle and terrifying form of warfare. Imagine you are a soldier in a besieging army, staring up at those towering timber walls. Unlike the predictable, static face of stone, this structure seems almost alive. The wind whispers through thousands of wooden joints, creating an eerie chorus of creaks and groans. Massive gates, sheathed in iron, swing open with a sound like a dying beast's roar, only to slam shut again, leaving you with a fleeting glimpse of the shadowy, complex interior. This wasn't just a barrier, it was a performance designed to unravel your nerve before a single arrow was ever loosed. The very architecture was a tool of psychological manipulation. Builders understood that intimidation was a weapon, and they crafted their fortresses accordingly. Many Slavic gords and Viking ring forts featured gatehouses adorned with fearsome carvings, snarling animal heads, grotesque faces, or symbols of protective deities. These weren't mere decorations, they were a deliberate message to any approaching force, a visual declaration that this place was under the watch of powerful, otherworldly guardians. The layout itself was a mind game. Where a stone castle might have a straightforward, imposing entrance, a wooden fortress often featured a labyrinthine approach, narrow, twisting corridors between inner and outer walls, confusing switchbacks and multiple choke points. An attacker charging through the breached outer gate wouldn't find a clear path to victory. They'd find themselves trapped in a deadly maze, disoriented and vulnerable, with defenders raining down projectiles from platforms they couldn't even see. This calculated unpredictability sowed doubt and hesitation, the two greatest enemies of a coordinated assault. Historical chronicles are filled with accounts of these psychological tactics in action. During the defense of a wooden fortress in the Hussite Wars, chroniclers described how the besieged defenders employed a terrifying array of sonic weapons to amplify the illusion of their strength. As enemy forces gathered under cover of darkness for a surprise attack, the defenders would suddenly erupt in a cacophony of noise, not just war cries, but the relentless beating of drums, the clashing of swords on shields, and the blaring of war horns from every corner of the fortification. This auditory assault created the overwhelming impression that the fortress was bursting with far more soldiers than it actually held, that its defenders were not fearful but ferociously confident. The effect on the morale of the attacking troops could be devastating, turning a stealthy advance into a chaotic retreat based on a perceived threat that was largely manufactured. This application of psychological pressure aligns perfectly with ancient military philosophy. The great strategist Sun Tzu wrote that the supreme art of war is to subdue the enemy without fighting, to break their will before engaging their army. Wooden fortresses were the physical embodiment of this principle. They presented a puzzle that was as much neurological as it was tactical. The flexibility of the walls meant that a successful breach might not lead to collapse but to a frustrating, elastic rebound. The ease of repair meant that a week's worth of battering could be nullified in a single night, a demoralizing sight that made an army's efforts feel utterly pointless. A stone wall, once cracked, offered the clear promise of imminent victory. A wooden wall, groaning and shifting but never failing, offered only the grim prospect of a protracted, exhausting siege with no guaranteed end, a battle of attrition that could break an army's spirit long before it broke the fortress's defenses. Moving west from the ring forts of Scandinavia, we find another breathtaking example of wooden engineering mastery, this time crowning the rolling green hills of Britain and Ireland. The Celtic hill forts, names like Maiden Castle in Dorset or Danebury in Hampshire, often conjure images of vast, grassy ramparts, ancient earthworks sculpted into the landscape. And while these monumental ditches and banks formed their formidable skeleton, it was the wooden structures upon them that gave these fortresses their teeth and their tenacious spirit. These were not simple earthen enclosures. They were sophisticated, multi-layered defensive complexes where timber, stone, and soil were woven together into a hybrid system of astounding resilience, a system that would famously test the might of the Roman war machine. The first thing to understand is the sheer scale of these constructions. Maiden Castle, for instance, is not a small outpost but a sprawling complex that encloses an area equivalent to 50 football pitches, its multiple concentric ramparts rising like waves across the hilltop. The earthworks alone are a stunning feat of labor, but they were just the foundation. Crowning these steep, man-made slopes were towering wooden palisades, walls of sharpened logs that could reach heights of 4 or 5 meters. But these were not simple fences. Archaeological evidence from sites across the UK shows these palisades were incredibly sophisticated. They were often double or even triple layered, with the gaps between the timber walls filled with rubble and soil, creating a massive composite barrier that was both immensely thick and surprisingly shock-absorbent. This design brilliantly merged the defensive qualities of all three materials. The earth bank provided a stable, immovable core that resisted tunneling and battering. The stone infill shattered sword edges and stopped projectiles, and the wooden facade offered that crucial flexibility, allowing the structure to shudder under impact without catastrophic failure. This hybrid approach proved devastatingly effective against a variety of threats, but its ultimate test came with the arrival of Rome's legions. The Roman army was a master of siegecraft, trained to overcome fixed fortifications with artillery, siege towers, and disciplined infantry assaults. Yet the Celtic hill forts, with their wooden-hearted defenses, presented a uniquely frustrating challenge. A Roman ballista bolt might thud into the earthen rampart and be swallowed whole, leaving barely a mark. A battering ram swung against the wooden palisade would find its force dissipated by the yielding timber and the immense, unyielding mass of earth behind it. Even if a section of the wall was set ablaze, the earth and stone core would often act as a firebreak, limiting the damage to a single, manageable section rather than allowing the flames to race along the entire perimeter. The Romans, used to breaching walls that broke, now faced walls that bent, absorbed, and could be repaired overnight. This capacity for rapid adaptation is what truly set the hill forts apart, a quality noted by preeminent historians like Barry Cunliffe. Unlike a static stone fort, which was essentially frozen in its original design, a hill fort was a living, evolving entity. If attackers developed a new tactic, perhaps focusing their assault on a particular gate or section of wall, the defenders could respond with astonishing speed. They could heighten the palisade in that sector, add an extra layer of timber reinforcement, or even build an entirely new, forward earthwork to break up an approaching formation, all within a matter of days or weeks. Excavations at countless sites reveal a history of constant modification and rebuilding. Post holes are found overlapping and cutting through earlier ones, showing that walls were deliberately torn down and repositioned. Gates were narrowed or reinforced, and new defensive lines were added in direct response to the lessons of previous attacks. This was defense as an ongoing conversation, not a monolithic statement. The enduring legacy of these sites, many of which remained occupied and militarily significant for over 1,000 years, is a powerful testament to the versatility and intelligence of this wooden earth-stone synergy. They were not defeated because their design was flawed. They were ultimately overcome by the overwhelming, systematic resources of an empire and the political changes it imposed. The Celtic hill fort stands as a monumental reminder that the most successful innovations are often those that embrace flexibility over rigidity and clever synthesis over reliance on a single, supposedly superior material. They teach us that true strength lies not in being unbreakable, but in being adaptable, in having the capacity to learn, change, and rebuild, a lesson carved not in stone, but in the resilient heart of timber and earth. But beyond the battlefield heroics and architectural genius, there was a more fundamental, earthbound reason for the triumph of timber: pure, unassailable economics. While a king or an emperor might commission a stone castle as a lasting monument to their dynasty, a wooden fortress was the pragmatic choice for survival, a tool of defense that was accessible to nearly any community with access to a forest and a determined population. The math was overwhelmingly simple. Constructing in stone was a generations-long financial black hole, a massive capital project that could bankrupt a treasury and tie up resources for decades. The sheer logistics were staggering. Quarrying the rock required specialized miners and explosive powders. Transporting it demanded teams of oxen and reinforced carts, often moving at a snail's pace over non-existent roads. Then came the masons, highly skilled and expensive artisans who would spend years, if not lifetimes, carefully shaping each block. The entire endeavor was a top-down affair, possible only for the most centralized and wealthy powers. Wood, by beautiful contrast, was a democratic material. In the vast forested stretches of medieval Europe and Asia, timber wasn't a luxury import. It was the very fabric of the landscape, a renewable resource that could be harvested, shaped, and assembled by the very people it was meant to protect. The labor force didn't require years of specialized apprenticeship. A village's carpenters, blacksmiths, and farmers, men who already understood how to work with wood and earth, could form the backbone of the construction crew. Their tools were simple and ubiquitous: axes, adzes, saws, and augers, items commonly found in any well-equipped settlement. This dramatically lowered the barrier to entry for defense. A local chieftain, a tribal elder, or a community council could organize the building of a formidable gourd or stockade without waiting for royal permission or draining their collective wealth. This wasn't just building, it was a community rising up to arm itself with the materials it had on hand. The difference in construction speed wasn't a matter of years, but of survival. When scouts brought word of an approaching raiding party or a migrating horde, time was the most precious commodity. A stone castle was a useless dream in such a moment. But a wooden fortress, chronicles from the period suggest that a motivated community could raise a basic but effective defensive palisade with earthworks in a matter of weeks. More sophisticated complexes, like a Viking ring fortress, could be completed in a single building season. This incredible speed turned wood into a strategic weapon in itself. It allowed a region to rapidly respond to a threat, creating a network of strongpoints that could slow down an invader, protect the local population and their harvest, and provide a base for counterattacks. An army on the move, expecting to find undefended villages ripe for plunder, would instead be confronted by a newly built wooden wall, behind which waited a prepared and defiant populace. This economic reality shaped the very strategies of history's great conquerors. The Mongol armies that swept across Asia and into Europe in the 13th century were masters of psychological warfare and understood logistics better than anyone. They quickly learned to prioritize their targets. A towering stone castle, while imposing, represented a massive, static investment. It couldn't be moved, and its loss was a catastrophic financial and symbolic blow to its owner. Destroying it could break the will of a region. A wooden fortress, however, was a more frustrating and elusive target. It was cheaper, faster to rebuild, and often part of a decentralized network. Burning one down was a temporary setback for the defenders, not a permanent victory for the Mongols. This is why historical accounts often note that the Mongols would bypass areas dominated by these agile wooden defenses in favor of delivering a decisive blow to the more prestigious, but ultimately more vulnerable stone citadels. When economic historians crunch the numbers, the scale of this advantage becomes astonishingly clear. Conservative estimates suggest that opting for a wooden fortress over a comparable stone structure could save a staggering 70% of the total cost. This wasn't just about saving money, it was about redistributing power. This cost efficiency effectively democratized defense. It meant that smaller political entities, independent towns, frontier baronies, tribal confederations, could maintain a credible defense against larger, wealthier neighbors or nomadic empires. They didn't need a king's treasury, they needed communal will and a good stand of oak trees. This practicality, this ability to provide serious security without requiring feudal-scale resources, is the unsung reason for the sheer ubiquity of wooden fortifications across the globe. They were the great equalizer, proving that resilience wasn't a luxury only the richest could afford, but an intelligent design anyone could build. Long before the iconic onion domes and red brick walls defined the Russian skyline, the heart of its defense pulsed with the strength of the forest. The very word Kremlin simply means fortress, and for centuries that fortress was built not of stone, but of towering, interlocked logs. These early wooden Kremlins were not crude prototypes. They were the sophisticated, dynamic nerve centers of Russian principalities, designed to thrive in one of the most unforgiving climates and face down the most relentless cavalry armies on Earth. They were fortresses built with a deep understanding of two things: the brutal Russian winter and the terrifying speed of nomadic horse archers. Their design was a direct response to these challenges, favoring rapid construction and strategic flexibility over permanent, static grandeur. Consider the sheer logistical nightmare of building with stone in medieval Russia. The deep winter freeze halted quarrying for months on end. Transporting immense blocks of stone across vast, roadless distances, through dense forests and over swampy ground, was a Herculean task that could consume a generation's wealth and labor. Wood, however, was everywhere. The endless taiga provided an inexhaustible supply of perfect, straight pine and oak. This abundance meant a prince or a town council could decide to fortify a strategic river junction or a hilltop and have a formidable defensive complex rising within a single building season. This speed was their ultimate strategic weapon. As Mongol scouts were spotted on the horizon, communities could funnel behind walls that seemed to sprout from the very soil, a testament to a culture that had mastered the art of building strong and building fast. The architecture of these wooden citadels was a marvel of multi-layered defense. They were not single walls but a series of concentric barriers, each one higher than the last, creating a deadly topographical puzzle for any attacker. The outer perimeter was often a sharpened palisade followed by a deep ditch, and then the main event, the massive tin wall. This was no simple fence. Built using the same intricate block-bow technique as the Slavic Gourds, it consisted of horizontally laid logs notched and locked at the corners into immense, stacked cribs. These cribs were often filled with a mixture of earth and stone, creating a composite structure that was both flexible and incredibly dense, able to absorb the impact of projectiles that would shatter pure masonry. At regular intervals, towering watchtowers called vežes jutted out from the walls. These weren't just for looking, they were heavily fortified archery platforms that provided overlapping fields of fire, ensuring that no approach to the wall was ever safe. But the true genius of these structures lay in their ingenious adaptations to the environment. One of the most brilliant features was the implementation of heated walls. In the depths of a Russian winter, a stone wall would become a sheet of ice, impossible for defenders to scale safely and offering a treacherous, slippery surface for determined attackers. Russian builders solved this by integrating a system of clay-lined wooden pipes or channels within the lower sections of the walls. During a siege, defenders would pour heated water or run heated stones through these channels, gently warming the wall just enough to prevent ice from forming. This kept the fighting platforms clear and secure, turning the harsh winter from a vulnerability into a defensive ally. Furthermore, the wooden shingle roofs covering the ramparts were designed with a steep pitch, causing heavy snow to slide off and preventing the immense weight from collapsing the structure, a simple yet vital detail stone battlements didn't require. Their tactical flexibility was perhaps their greatest asset, perfectly demonstrated during the Mongol invasions. When the armies of Batu Khan swept across the Rus principalities in the 13th century, they encountered both stone and wooden fortresses. The chronicles tell a revealing story. The stone castles, for all their imposing permanence, often proved to be brittle tombs. Once the Mongols' Chinese siege engineers breached a section of wall with their catapults, the defense typically collapsed. The rigid stone could not be repaired, and the breach became a permanent funnel for the invaders. Wooden Kremlins, however, told a different tale. The same bombardment would create a splintered, mangled section of wall, but rarely a clean, wide-open breach. More importantly, the damage was repairable, often under cover of darkness. Prefabricated panels of log cribbing could be maneuvered into place to seal a gap, and the earthen infill meant that even a partially destroyed section could be quickly shored up with earth-filled baskets to form a new, temporary bulwark. This ability to heal overnight drove besiegers to despair. The chronicles of the defense of towns like Kozulsk and Ryazan, though ultimately tragic, are filled with accounts of these wooden fortresses holding out for weeks against overwhelming odds, their defenders using a network of hidden sally ports to launch devastating guerrilla attacks. These were small, cleverly concealed doors within the walls, often hidden by vegetation or built below the waterline of a moat. Under the veil of night or a diversionary attack, squads of warriors would erupt from these hidden exits, striking at the Mongol siege lines, burning their equipment, and vanishing back into the fortress before a proper counterattack could be organized. This constant, unpredictable aggression pinned down large enemy forces and stretched sieges out far longer than the Mongols were accustomed to. The wooden Kremlin was not a passive shield. It was an active, responsive instrument of war, a testament to a defensive philosophy that valued adaptability and cunning just as highly as brute strength. Of all the threats a wooden fortress could face, fire was the most terrifying specter, the one weakness every attacker aimed to exploit and every defender feared. It's the first assumption we make today. Of course, a castle made of wood would burn. This perception has persisted for centuries, cementing the idea that these structures were inherently fragile and temporary. But this simplistic view ignores a far more fascinating reality. The builders of these wooden marvels were not naive. They were brilliant pragmatists who stared their greatest vulnerability in the face and engineered a stunning array of solutions to combat it. They didn't just hope their walls wouldn't catch fire. They designed them from the ground up to resist, slow, and ultimately survive the flames. The first line of defense was in the very selection and preparation of the timber itself. Builders were masters of their material and knew that not all wood burns the same. They often preferred dense, resinous hardwoods like oak, which are naturally more resistant to ignition than softer woods like pine. More importantly, they frequently used wood in its green state, freshly cut and still saturated with natural sap and moisture. Try lighting a campfire with a freshly cut, wet log. It's a lesson in frustration, producing more hissing steam than actual flame. This green timber was incredibly difficult to set ablaze with the limited incendiary weapons of the era, such as fire arrows or torches. The outer surface might char and blacken, but the moisture deep within the log would prevent the fire from taking hold and spreading, often causing an arrow to simply fizzle out on impact. Beyond choosing the right wood, builders applied sophisticated chemical and physical barriers. One of the most common techniques was daubing, coating the exterior wooden surfaces with a thick layer of wet clay, mud, or a lime-based whitewash. This created a fireproof crust that shielded the flammable wood beneath from direct contact with flames. This wasn't a flimsy layer of paint. It was a substantial, inches-thick application that had to be regularly maintained. In many Slavic gourds, this daub was mixed with horsehair or straw for added structural integrity, effectively turning the wooden wall into a form of primitive, fire-resistant composite material. In Japan, the plaster walls of a Yamashiro served this exact same purpose, creating a beautiful white exterior that was also a highly functional layer of protection. The architecture itself was also designed with fire suppression in mind. Some of the most ingenious fortresses incorporated water channels or hollow sections within their walls. Imagine a wooden palisade built with a narrow gutter running along its top, kept filled with water from a diverted spring or a well within the compound. During a fire attack, defenders could simply scoop from this ready reservoir to douse flames. More complex systems, hinted at in some archaeological finds, suggest that certain structures may have had hollow logs or pipes integrated into their design, allowing water to be poured down from above onto specific burning sections, functioning as a primitive but effective built-in sprinkler system. Of course, technology alone wasn't enough. It was backed by rigorous training and organization. A wooden fortress under siege would have dedicated firefighting teams, a constant watch whose sole job was to patrol the ramparts with buckets of water, sand, and wet hides. At the first sign of a flame, these teams would swarm the area, smothering the threat before it could gain a foothold. They also engaged in proactive defense, soaking the exterior walls and roofs before a major assault was expected, making them even more resistant to ignition. This relentless vigilance turned the fortress into a living entity that could actively fight back against its own destruction. The historical record is filled with powerful testimonies to the effectiveness of these measures. The siege of Kozulsk in 1238 during the Mongol invasion is a prime example. The Mongols were masters of siege warfare and would have undoubtedly used fire as a primary weapon against the wooden walls of this ruse stronghold. Yet, chronicles note that the defenders held out for an astonishing 7 weeks. The fortress did not fall to a conflagration. It was ultimately overwhelmed by sheer numbers and relentless bombardment after a protracted and heroic defense. The wood, treated and defended with ingenuity, did not betray them. In a tragic irony, it was often stone castles that suffered more catastrophic damage from fire. The intense heat of a major blaze could heat the stones to a point where they would crack and shatter, and the mortar holding them together could calcify and turn to powder, causing entire sections of wall to collapse inward, a failure mode that a flexible, earth-backed wooden wall simply did not have. As fortress historian Cathcart King and others have argued, this collective evidence forces us to drastically reevaluate the perceived vulnerability of wood. Fire was not an automatic death sentence. It was a calculated risk, a known threat that was met with a sophisticated, multi-layered defense system. The builders transformed a glaring weakness into a managed variable, something to be planned for, mitigated, and controlled. This shift in perspective is crucial. It moves these structures out of the category of primitive and risky and into their rightful place as highly evolved, intelligent responses to the challenges of medieval warfare. The true marvel isn't that they were built of wood, but that they were built so well that even their greatest weakness could be engineered into near obsolescence. Across the Atlantic, in the vast and varied landscapes of North America, a parallel tradition of wooden fortification was reaching its zenith, one born from an intimate knowledge of the forest and a pressing need to defend homeland from a new kind of threat. The indigenous nations, from the powerful Iroquois Confederacy in the northeast to the Cherokee in the southeast, were already master builders of palisaded towns, structures that served as community hubs and defensive bastions long before European ships appeared on the horizon. When those colonists did arrive, armed with unfamiliar weapons and tactics, they expected to easily overrun what they dismissively viewed as primitive villages. Instead, they were met with a rude awakening, confronting sophisticated wooden fortresses whose design was perfectly honed for the realities of North American warfare, turning the dense woodlands from an obstacle into an impenetrable shield. The classic Native American stockade was a masterpiece of environmental integration. Unlike the geometric precision of a Viking ring fort or the grand earthworks of a Celtic hill fort, these structures flowed with the natural topography. Builders would strategically place their town on a high bluff overlooking a river or tuck it into a bend of a creek, using the water as a natural moat that protected one or more sides. The side facing the land, the most vulnerable approach, would then be defended by the palisade itself. But this was no simple row of pointed sticks. The most common and effective design was the double-walled stockade. Two parallel rows of massive, vertically set logs were driven deep into the earth, spaced several feet apart. This gap was then filled to the brim with a mixture of earth, stone, and rubble, creating a wall that was not only incredibly thick, often 6 to 10 feet across, but also possessed the same brilliant shock-absorbing qualities as the Slavic gords. A musket ball would bury itself harmlessly in this dense pack. Even a small cannonball would only succeed in splintering the outer layer of logs, leaving the earthen core largely intact and easily repairable. Upon this formidable base, defenders built a sophisticated fighting platform. The horizontal beams connecting the tops of the inner and outer log walls created a sturdy walkway that ran the entire circumference of the settlement. From this elevated position, warriors could fire arrows or, later, trade muskets through loopholes left in the inner wall, enjoying excellent protection while having a commanding field of fire over the approaches. At the corners and above the main gates, these platforms often expanded into projecting bastions or watchtowers. These allowed defenders to fire along the exterior face of the wall, creating a deadly crossfire that could rake any attacker who managed to get close to the palisade, eliminating the defensive blind spots that plagued simpler square design. The psychological and tactical impact on European colonists was profound and is vividly recorded in their own, often frustrated accounts. The settlers at Jamestown, Virginia, provided some of the most detailed descriptions. They wrote of the Powhatan villages surrounded by these palisados as being very strong and very difficult to assault. Captain John Smith himself noted the resilience of these structures, describing how their arrows and early gunfire seemed to have little effect. The settlers, trained in the European tradition of besieging stone castles or fighting in open fields, found themselves completely outmatched by this style of forest warfare. Their heavy armor was a hindrance in the dense woods, their linear tactics useless against defenders who used the stockade and the surrounding forest as a unified defensive system. Attacks would often disintegrate into a chaotic nightmare, with colonists being harried by snipers from the trees long before they even reached the wall, only to be met with a withering hail of projectiles from the protected platforms above. The defense of the Cherokee town of Nequessee against British forces in the early 18th century stands as a powerful testament to their effectiveness. The Cherokee, under immense pressure from colonial expansion, had fortified their key towns with these advanced stockades. when a British expeditionary force, confident in its superior firepower, laid siege to one of these strongholds, they found their cannonade had a disappointingly limited effect. The wooden walls would splinter and give way in sections, but the packed earth core prevented a clean breach. Meanwhile, Cherokee warriors used well-concealed sally ports to launch devastating raids on the British siege lines under cover of darkness, destroying supplies and keeping the attackers in a constant state of anxiety. The siege dragged on far longer than British commanders had anticipated, draining their resources and morale, and ultimately forcing a negotiated settlement rather than the decisive victory they had expected. This story, repeated in various forms across the continent, proves that these were not just fences but highly evolved fortresses that enabled indigenous nations to protect their sovereignty and way of life against overwhelming odds for generations. So if wooden fortresses were so brilliantly effective, so strategically adaptable, and so widely successful across the globe, why did they vanish from the historical spotlight, overshadowed completely by the cold, hard permanence of stone? The answer lies not in a tale of superior technology, but in a far more human story of power, prestige, and the politics of memory. The shift from wood to stone was never a simple upgrade. It was a profound cultural and political transformation, where the practical genius of the carpenter was slowly eclipsed by the symbolic power of the mason. This transition began with the slow crystallization of feudal power structures. As local chieftains evolved into kings and emperors, their need to project an image of unassailable, eternal authority became paramount. A mighty stone castle, rising from the landscape with seemingly impossible weight and permanence, was the ultimate billboard for this new kind of power. It screamed stability, legacy, and divine right in a way that a wooden fortress, no matter how resilient, simply could not. Wood was the material of the pragmatic defender. Stone was the material of the ambitious dynast, a literal monument to their name meant to endure for centuries. This symbolic shift was powerfully accelerated by the arrival of a technological revolution, gunpowder artillery. The first cannons that rumbled onto European battlefields in the 14th century were erratic, slow-firing beasts, and ironically, they initially struggled more against wooden walls than stone. A stone wall, when hit by an early cannonball, would crack, splinter, and send deadly shards of masonry flying inward. A thick, earth-backed wooden wall, however, would often absorb the impact with a deep, splintering groan, and the soft iron or stone shot itself would frequently shatter on impact. Yet, as gunpowder technology advanced rapidly, the rules of defense changed. The solution to more powerful cannons was not flexibility, but sheer mass walls needed to be lower, thicker, and sloped to deflect shot. This new engineering challenge, known as the Trace Italian or Star Fort style, was answered with earth and brick, materials that could be shaped into these new geometric forms. While wood could be and was incorporated into these new designs as reinforcement, the era of the standalone wooden fortress as the pinnacle of defense was drawing to a close, not because it was obsolete, but because the entire paradigm of warfare was shifting beneath the feet of its builders. Perhaps the most decisive factor in the disappearance of wooden fortresses from our collective memory, however, was the bias of the historical record itself. Medieval chroniclers were most often employed by the very kings and nobles who were building these grand stone castles. Their job was to glorify their patron's legacy, to write a history that would echo through the ages, celebrating the majesty and permanence of their rule. What better symbol than a towering stone keep? These scribes meticulously documented the construction of stone marvels, the sieges they endured, and the dynasties they protected. The humble wooden fortress, by contrast, was the defense of the common folk, the frontier town, the smaller lord. Its stories were passed down through oral tradition or recorded in local letters that were far more likely to be lost to fire, rot, or simply the passage of time. History, as the saying goes, is written by the victors, and in this case, the victors were the centralized states who built in stone, and they wrote a history that conveniently forgot the wooden strongholds that had often saved their predecessors. This historical amnesia was then cemented by archaeology itself. For centuries, the very nature of these materials dictated what we could find. A stone castle, even in ruins, leaves an unmistakable skeleton upon the landscape piles of carved rock that shout their presence across millennia. A wooden fortress, however, vanishes almost completely. When abandoned, its mighty timbers are carted away for reuse, rot back into the soil, or are consumed by fire, leaving behind only subtle ghosts, discolored soil where posts once stood, faint outlines of ditches and patterns of post holes. Until the advent of modern archaeological techniques like aerial photography, ground-penetrating radar, and meticulous soil analysis, these traces were incredibly easy to overlook. The grand narrative of military architecture was therefore built almost entirely on the evidence that was easiest to see. The stone that remained, the wood which had returned to the earth, took its secrets with it, creating a vast blind spot in our understanding of the past. We are now finally in the midst of a great correction. Modern archaeology is acting as a time machine, using technology to read the landscape in ways previous generations could not. The LiDAR scan that reveals the perfect circle of a Viking ring fort under a Danish farmer's field, the painstaking excavation that maps the intricate post-hole patterns of a Slavic gourd, the soil analysis that proves the existence of a massive wooden palisade around a Native American town. Each of these discoveries is rewriting the history books. They are proving that these structures were not rare exceptions, but were often the dominant form of defense for vast stretches of history and across continents. This isn't just about adding a footnote. It's about fundamentally rebalancing our understanding of the past, shifting credit from the static symbols of power to the dynamic, intelligent, and resilient designs that truly define defense for most of human history. The story of the wooden fortress is a powerful reminder that what endures in stone is not always what was most effective in its time, and that true innovation is often found in the pragmatic and adaptable, not just the monumental and permanent. While the Celts perfected the art of the hybrid hill fort and Native Americans turned the forest itself into a weapon, another empire was mastering wooden engineering on a breathtaking scale, using it not just to defend but to conquer. The Ottoman Empire, at the zenith of its expansionist power in the 16th century, faced a formidable logistical nightmare: how to project control over the vast, restive territories of the Balkans, often hundreds of miles from their central supply bases. Their brilliant solution was not to build eternal stone citadels, but to unleash a wave of rapidly deployable wooden strongholds known as Palankas. These were not fortresses in the traditional, sedentary sense. They were instruments of mobile domination, designed to be planted into contested soil with the speed and precision of a military campaign itself, demonstrating that the most effective form of control could be both temporary and terrifyingly effective. The core innovation of the Palanka system was radical prefabrication. Ottoman military engineers perfected a process where key components of these fortresses were manufactured in centralized workshops far behind the front lines. Imagine vast depots where teams of carpenters mass-produced standardized wooden panels, pre-cut gatehouse elements, and pre-assembled watchtower sections. These components were then meticulously numbered, organized, and loaded onto a dedicated train of ox carts that followed the advancing Ottoman army. when the commander selected a strategic location, a vital mountain pass, a crucial river ford, a crossroads controlling a valley, the construction corps would swing into action. Unlike a stone fortress which required skilled masons and years of labor, the palanca could be assembled by soldiers following simple instructions, slotting the pre-made pieces together like a giant, lethal puzzle. What took generations for a medieval kingdom, the Ottomans could achieve in a matter of weeks, suddenly materializing a fully garrisoned strongpoint in what had been empty land just a month before. The design of these prefabricated forts was a masterclass in anticipating the evolving battlefield. As gunpowder artillery became more common, the palanca evolved to meet the threat. Their walls were not simple vertical palisades. They were often built at a sharp angle or with a distinct outward slope. This clever geometry was a primitive form of ballistic armor. When a cannonball struck an angled wooden surface, the impact was more likely to be a glancing blow, deflecting its energy sideways and upwards rather than allowing it to punch straight through. This was a feature that many older, vertical-walled stone forts lacked, making them ironically more vulnerable to the new artillery. Furthermore, the palanca's wooden construction was its own form of defense against cannon fire. A stone wall, when hit, would crack and send lethal shards of shrapnel flying inward. A wooden wall would splinter and absorb the shot, and the damage could often be patched overnight with a fresh, pre-cut panel, a repair job utterly impossible with shattered masonry. Historical records from the Habsburg-Ottoman frontier wars are filled with frustrated accounts that testify to the palanca's effectiveness. European armies marching to relieve a besieged town or confront an Ottoman field army would constantly find their lines of communication and supply harassed by these sudden wooden obstacles. A large force would have to stop and lay a formal siege to reduce the palanca, a time-consuming process that threw entire campaign timetables into disarray and drained precious resources. Smaller detachments would find themselves unable to dislodge the garrison at all. This was the palanca's primary strategic role. It acted as a breakwater, slowing the tide of any Christian counter-offensive, channeling enemy movements into predictable paths where they could be ambushed by Ottoman cavalry, and buying invaluable time for the main Ottoman forces to concentrate and strike. They were the ultimate delay mechanism, turning the very landscape into a hostile, fortified environment for their enemies. This logistical and tactical genius reveals a profound Ottoman understanding of imperial power. While they certainly built magnificent and permanent stone fortresses in key cities like Belgrade or Buda, their true strength in the frontier regions lay in this philosophy of agile, renewable defense. The palanca allowed them to hold territory with a surprisingly small investment of permanent resources. If a palanca was eventually destroyed by a massive enemy effort, it was not a catastrophic loss. The garrison would withdraw, the knowledge would be retained, and a new one could be built elsewhere just as quickly. This system turned defense into an offensive tool, enabling one of history's most rapid and successful military expansions. The humble wooden palanca stands as a powerful testament to the idea that speed, adaptability, and intelligent logistics can often achieve far more than the most imposing and permanent monument of stone. For centuries, the superiority of wooden fortresses was a story told through chronicles and archaeology, a narrative of observed results. But why did they work so well? Today, we're no longer relying on historical accounts alone. We can put these ancient materials to the test with the full force of modern science, and the results are confirming that medieval builders possessed an almost intuitive genius for material physics. The secret isn't just in the grand design of the walls, but in the microscopic world of the wood itself. At a cellular level, wood is a natural composite material, a complex matrix of strong cellulose fibers held together by a softer substance called lignin. This structure is not monolithic and brittle like stone. It's a dense network of tiny tubes and chambers. When a sudden force impacts it, like a catapult stone or a battering ram, this cellular network acts like a biological shock absorber. The cells compress, buckle, and deform, dissipating the kinetic energy of the blow throughout a large volume of the material. Instead of transmitting that energy in a straight line to create a single, catastrophic crack as stone does, wood turns that destructive force into a multitude of tiny, internal failures. It sacrifices a small area to save the whole structure, bending so it does not break. This principle is dramatically illustrated by modern engineering tests. Researchers at institutions like the University of Cambridge have moved beyond theory, constructing replica medieval walls and subjecting them to controlled projectile impacts. Using high-speed cameras and strain gauges, they can measure exactly how these structures react. The footage is startling. A stone wall, when struck, behaves precisely as expected. The energy transfers instantly, creating a localized explosion of fragments and a clear breach. A wooden wall, however, tells a different story. It visibly shudders and recoils, the impact creating a deep, splintered dent but rarely a clean puncture. The wall might be wounded, but it remains standing, and most importantly, it remains structurally cohesive. The damage is contained. This containment is the key to its repairability. A section of shattered stone must be completely rebuilt from the ground up, a task impossible during a siege. A dented wooden panel, however, can be braced, patched, or even replaced overnight with a prefabricated unit, a tactical advantage that scientific modeling now proves was absolutely decisive. Beyond its innate impact resistance, wood's longevity was another puzzle that modern chemistry has helped to solve. We've long assumed that a wooden structure must be inherently temporary, doomed to rot and insect infestation within a few decades. Yet, we know historically that many of these fortresses stood for generations. How ancient builders developed empirical chemical treatments that profoundly enhanced wood's durability. One of the most widespread and effective techniques was surface charring. By carefully burning the outer layer of a timber post or beam, they weren't just blackening it, they were transforming its chemical composition. The heat drives out moisture and converts the surface cellulose into a form of carbon that is no longer palatable to fungi or insects. This charred layer, often then coated with tar or animal fat, created a hardened, waterproof shell that protected the still resilient wood within. It's a process remarkably similar to the Japanese shu-sugi-ban technique, which is now celebrated in modern, sustainable architecture for the very same reasons. Similarly, the practice of immersing wood in oil or brine was a primitive but highly effective form of polymer stabilization. Soaking timber in linseed oil or tallow forced these substances deep into the cellular structure, displacing air and water that would support rot. In coastal regions, soaking wood in saltwater pools before use saturated it with salt, making it completely unappetizing to termites and wood-boring beetles. These weren't just folk remedies, they were deliberate preservation strategies that extended the functional lifespan of a wooden fortress from a few years to many decades, sometimes even centuries. Modern material scientists analyzing treated samples from archaeological sites are consistently impressed by the efficacy of these methods, which effectively created a composite material, wood enhanced with natural preservatives, that was perfectly suited to its environment. What emerges from this scientific scrutiny is a profound respect for the engineering intellect of the past. These builders didn't have electron microscopes or finite element analysis software, but they had something equally powerful: generations of meticulous observation and hands-on experimentation. They learned which tree species had the toughest, most flexible fibers, they discovered through trial and error how to join them to maximize strength and how to treat them to defy decay. They weren't just stacking logs, they were manipulating the very properties of their material to achieve a desired performance under extreme stress. Modern science hasn't debunked their methods, it has validated them, revealing a deep, empirical understanding of material mechanics that was centuries ahead of the formal theories that would eventually explain why their incredible structures worked so well. This bridge between ancient craft and modern analysis shows us that their brilliance wasn't a mystery, it was applied physics, honed to a razor's edge by necessity. When we picture the Great Wall of China, our minds instantly conjure an endless, serpentine ribbon of stone and brick, snaking across mountain peaks and deserts, a seemingly permanent and immutable barrier carved into the earth. This iconic image, however, tells only the final chapter of a much longer and more dynamic story. Long before the Ming dynasty committed its immense resources to masonry, the frontier defenses in the most remote and challenging regions were built from a more adaptable, more intelligent material, wood. In the dense forests of Manchuria and the rugged, inaccessible terrain where transporting stone was a logistical nightmare, Chinese military engineers turned to the abundant timber to create a defensive system that was not a static wall, but a living, responsive organism. These wooden frontier fortresses were the agile, flexible precursors to the stone monolith, designed to handle the constant, low-level threat of nomadic raids with an efficiency and cleverness that rigid stone could never match. The design philosophy here was fundamentally different from building a single, continuous barrier. It was about creating a network of control. Instead of one unbreakable line, engineers constructed a series of wooden watchtowers and fortified outposts at strategic intervals commanding high ground, overlooking river crossings and blocking known invasion paths. These towers were not lonely sentinels, they were interconnected hubs capable of communicating via signal fires or flags, creating a web of awareness that could track and respond to enemy movements across a vast territory. The walls connecting them were often palisades of sharpened timber, but their true strength lay in their modularity. If a raiding party managed to burn or break through a section, it wasn't a catastrophic failure. The damage was localized. Pre-cut replacement timbers could be swiftly brought up from a rear depot, and the breach could be repaired in a matter of days, sometimes even hours. This was a defense designed with an understanding that perfection is impossible. Instead, it prioritized resilience and rapid recovery, ensuring the network as a whole could never be permanently severed by a single attack. Within these wooden strongholds, Chinese ingenuity produced some of the most deviously clever defensive features ever conceived. Ming Dynasty texts describe mechanisms that sound like they belong in a thrilling wuxia novel, yet they were very real. Certain gatehouses were equipped with massive, counterweighted swinging gates. An attacking force, believing they had stormed the main entrance, would find themselves funneled into a narrow killing zone, only for a second, hidden gate to swing shut behind them, trapping them inside where they could be annihilated from platforms above. Even more terrifying were the trap floors. Some elevated walkways and platforms within the fortresses were designed with pivoting sections or false panels. At a signal, defenders could release a latch, causing a segment of the floor to drop away, plunging invaders who had gained a foothold into a concealed pit below, often lined with sharpened stakes. These were not brute force defenses, they were psychological and tactical masterpieces, turning the fortress itself into an active participant in the battle, capable of deception, ambush, and controlled chaos in a way that a sheer stone wall could never emulate. This strategic use of wood was also a concession to the brutal realities of the northern climate. In the freezing winters of Manchuria, stone construction presented a hidden vulnerability. The mortar holding the blocks together could be compromised by moisture seeping into tiny cracks, freezing, and expanding over countless cycles. This insidious process, known as frost weathering, would slowly but surely degrade a stone wall from within, requiring constant, skilled maintenance. A wooden structure, particularly one built with treated timbers and complex joinery that allowed for expansion and contraction, was far less susceptible to this kind of damage. While individual timbers might need replacement, the overall structure remained sound. Furthermore, when damage did occur, it didn't require a team of highly specialized stonemasons to fix. Any competent soldier or local carpenter could wield an axe and a mallet, making repairs quickly and keeping the fortress operational. This ease of maintenance meant that in the most isolated and climatically harsh sectors, the wooden sections of the frontier often had a higher state of readiness and remained serviceable long after neglected stone sections had begun to crumble into disrepair. The story of the Great Wall, therefore, is not a simple replacement of an inferior wood with a superior stone. It is a story of hybridization and intelligent adaptation. The Ming Dynasty's monumental project in stone didn't erase the earlier wooden systems. It built upon the knowledge they provided, the strategic locations of watchtowers, the optimal placement for fields of fire, the understanding of invasion routes. All of this was learned and refined through generations of experience with the wooden frontier network. The stone wall became the enduring backbone, the symbol of imperial power meant to last for the ages. But it was the spirit of the wooden fortresses, their flexibility, their cleverness, their resilience, that informed its tactical soul. This chapter forces us to expand our view of history's greatest defensive line, revealing it not as a single, static entity, but as an evolving system that wisely used the right material for the right job, blending the permanence of stone with the agile intelligence of wood to create a defense that was truly greater than the sum of its parts. Yet the true power of these stories was not just in their ability to inspire awe, but to encode vital cultural values and survival knowledge. A Slavic folktale might not just speak of an immortal gourd, but would intricately describe the specific type of wood used for its gates or the clever design of its hidden water source, passing down practical engineering wisdom in the guise of a magical story. These narratives served as a communal blueprint for resilience, teaching each new generation that their safety depended not on impenetrable stone, but on collective wit, skilled craftsmanship, and an intimate knowledge of their natural environment. The fortress was more than a setting for these myths. It was the central character, a silent teacher whose wooden walls whispered lessons about preparation, unity, and the intelligent application of strength. In a world without formal academies, these legendary fortresses became the textbooks from which a people learned how to endure. This intertwining of myth and identity is powerfully illustrated in the Norse sagas, where the ring fortresses are often depicted not as human constructions, but as direct gifts from the gods or the work of legendary beings. The saga of King Harald Bluetooth and the construction of fortresses like Trelleborg is shrouded in this divine aura, suggesting that such perfect geometry and formidable strength could not be the product of mere mortals, but required the intervention of Odin's wisdom or the strength of Thor. By anchoring these structures in the realm of the divine, the stories elevated them beyond military hardware to become sacred symbols of order and cosmic power imposed upon a chaotic world. They were proof that a people were favored by the gods, that their kingdom was a deliberate part of a grand, celestial design. This spiritual significance made the defense of a fortress a sacred duty, its loss not just a tactical defeat, but a spiritual crisis that could shake the very foundation of a community's belief in its own destiny. In Japan, the legends surrounding Yamashiro took on a more spectral, yet equally powerful, dimension. Many tales speak of castles like Matsumoto or Heimji being defended not just by living samurai, but by the restless spirits of fallen warriors who refused to abandon their post. These ghostly guardians, known as yurei, were said to appear on the moonlit wooden parapets, their ethereal forms a warning to any who would threaten the sanctity of the place they died for. This wasn't merely a ghost story, it was a profound expression of the samurai code, Bushido, which valued loyalty and honor even beyond death. The wooden fortress became a physical anchor for the soul of a clan, a place where the courage of ancestors was believed to literally haunt the halls, inspiring the living to equal valor. The very creaks and groans of the old timber at night were interpreted not as the natural settling of wood, but as the whispers of these eternal sentinels, forever bound to the structure they loved more than life itself. The cultural footprint of these wooden marvels extended even into the foundational myths of empires. In Russia, the legend of the founding of Kiev tells of three brothers, Ki, Shchek, and Koriv, who built a fortified wooden town on the hills above the Dnieper River, a settlement that would eventually become the mother of all Russian cities. This story transforms the act of building a wooden gourd into a nation's creation myth, framing the first act of civilization not as the discovery of a place, but as the construction of its defense. The message was clear: community, identity, and safety were born simultaneously from the act of raising a wooden wall together. Similarly, in the Celtic traditions of Britain and Ireland, many ancient hill forts are referred to in folklore as the homes of fairy kings or the entryways to the otherworld, their earthen and wooden ramparts marking the boundary between the mundane human realm and a world of magic and danger. This attribution of otherworldly power to these sites ensured they were treated with a respect and awe that persisted long after their military function had faded, preserving them in the landscape as sacred hills long after their timber had returned to the soil. Ultimately, these myths and legends were the final, and perhaps most enduring, line of defense for the wooden fortress. Long after the last palisade had rotted away and the last watchtower had collapsed, the stories remained. They kept the memory of those structures alive, not as historical footnotes, but as vibrant symbols of what a community could achieve when faced with impossible odds. They taught that true strength was found in ingenuity and unity, that a well-made joint could be as powerful as a god's blessing, and that the spirit of a people could become so intertwined with the wood they shaped that it would endure for centuries, haunting the very imagination of their descendants. The legacy of the wooden fortress, therefore, is not measured in the years it stood, but in the timeless stories it inspired, proving that the most resilient materials of all are those carved not from timber, but from memory and myth. While European kings were raising their stone cathedrals and Japanese shoguns were perfecting their earthquake-resistant joinery, on the other side of the world, in the lush rainforests of West Africa, another civilization was achieving a feat of defensive engineering so monumental it would eventually be labeled the largest earthworks in the world undertaken by humankind. The Kingdom of Benin, flourishing in what is now southern Nigeria, did not just build a fortress, they sculpted their entire territory into a fortified landscape, constructing a vast network of immense banks and deep ditches, all crowned with formidable wooden palisades. This was not a single structure to be besieged, but an entire country engineered for deterrence, a sprawling system of defense that would successfully protect one of Africa's most powerful and sophisticated states for over 400 years from the escalating threat of European invasion. The scale of this undertaking is almost incomprehensible to the modern mind. Current archaeological surveys estimate that the total length of the earthworks built by the Benin Empire stretches for an astonishing 16,000 kilometers. To put that in perspective, that's a distance longer than the entire Great Wall of China, and it was excavated and piled by hand using iron shovels and baskets. This was not a haphazard digging of ditches. It was a deliberate, coordinated project that transformed the very geography of the region. The primary defensive element was the massive, vertical-sided ditch, which could be up to 20 meters deep in some sections. The earth excavated from this colossal trench was then piled high on the inner side to form an equally imposing rampart. This created a formidable physical barrier, but the Benin engineers were just getting started. Crowning these earthen walls was a bristling palisade of massive, sharpened timber posts, creating a continuous wooden wall that ran for miles across the top of the rampart, providing a protected fighting platform for the kingdom's soldiers. The sophistication of this design lay in its deadly integration of multiple defensive layers, each one designed to break an attacking force in a different way. The approach to the walls was itself a gauntlet. The ground in front of the main ditches was often seeded with sharp, concealed stakes, a primitive but devastating minefield to disrupt cavalry charges and infantry formations. Then came the main ditch, an obstacle so deep and steep that it would require scaling ladders just to reach the base of the inner rampart, all while attackers were exposed to a relentless hail of projectiles from above. But perhaps the most ingenious feature was the strategic use of the rampart's profile. In many sections, the inner face of the ditch was deliberately cut steeper than the outer face of the bank. This created a deadly kill zone at the bottom of the trench. If an attacker somehow managed to descend into the ditch, they would find themselves trapped in a deep pit, unable to scale the near-vertical inner wall while being completely exposed to defenders on the palisade above. It was a topographic trap of devastating efficiency. The reaction of the first Europeans to witness this marvel firsthand was one of pure, unadulterated awe. Portuguese explorers arriving by sea in the late 15th century were among the first outsiders to document the kingdom. These were men familiar with the stout stone castles of Europe, and they expected to find something less. What they found instead utterly confounded their expectations. Their accounts, preserved in ship logs and letters, describe a capital city surrounded by this massive, gated earthwork with wide, straight streets and a highly organized layout that spoke of a powerful, centralized authority. They wrote of the immense walls and the sheer hard work their construction must have required, expressing a respect that was often withheld from other non-European cultures they encountered. Some explicitly described the defenses as impregnable, a stunning admission from representatives of a continent that believed itself to be the pinnacle of military and architectural achievement. They had encountered not a primitive stockade, but a defensive complex that was every bit the equal of anything found in Portugal or Spain, yet conceived from a completely different philosophy and built entirely from local materials. The story of the Benin earthworks is perhaps the most powerful argument against the outdated and erroneous Eurocentric view of history that long positioned European technology as inherently superior. Here was a kingdom that, entirely independent of outside influence, developed a unique and phenomenally effective solution to the problem of defense, one that was perfectly adapted to its environment, resources, and the specific threats it faced. They used what they had in abundance, earth and wood, and through sheer manpower and brilliant organization, turned them into a barrier that defined and protected a nation for centuries. This wasn't a failed attempt to build a European-style castle. It was a parallel and in many ways superior innovation in military architecture. Its eventual fall to a British punitive expedition in 1897 had nothing to do with any weakness in its ancient design, but was a result of overwhelming technological disparity, the advent of Maxim guns and heavy artillery against which no pre-industrial fortress, whether of African earth or European stone, could ultimately stand. The legacy of Benin's walls forces us to dramatically widen our view of engineering history, recognizing that genius is not the monopoly of any one culture, but a universal human trait that flourishes wherever there is a need to protect what is most valued. But the true downfall of the wooden fortress wasn't heralded by a single, thunderous cannon shot. It was a slower, more complex shift, a transformation in the very philosophy of warfare and power that gradually pushed these resilient structures to the sidelines. The advent of heavy artillery did indeed change the calculus of defense, but not in the straightforward way we often imagine. The earliest bombards and cannons of the 14th and 15th centuries were wildly inaccurate, slow to reload, and often more dangerous to their crews than to the walls they targeted. Against a stone castle, these primitive guns could be devastating, as their iron balls would strike the rigid masonry and send lethal shards of stone flying like shrapnel, collapsing entire sections of wall in a cloud of dust. A wooden fortress with its flexible, earth-backed walls often fared surprisingly well against this initial artillery. The cannonball would thud into the timber, creating a spectacular shower of splinters and a deep, mangled wound, but it rarely created the clean, exploitable breach that besiegers needed. The wall would shudder and groan, but it would often hold, and that damage could be patched under cover of darkness. For a time, it seemed wood might even adapt to the age of gunpowder. The real change came with the relentless refinement of artillery. By the 16th century, cannons were becoming more powerful, more accurate, and more mobile. Foundries learned to cast barrels from stronger bronze and iron, allowing for larger powder charges and heavier shot. The development of standardized corned gunpowder provided a more consistent and powerful explosive force. Now, a well-aimed barrage from these new guns could not just dent a wooden wall. It could systematically pound it into kindling. The sheer kinetic energy of repeated impacts from 32-pound iron balls would eventually overwhelm the wood's ability to flex and absorb, reducing even the thickest timbers to a shattered mess. Furthermore, the increased use of incendiary shells, red-hot cannonballs heated in special furnaces, turned the ancient fear of fire into a far more potent and deliverable threat. A fortress that could withstand a volley of solid shot might be utterly consumed by a barrage of these fiery projectiles. Yet, to focus solely on technology is to miss the deeper, more profound revolution that sealed the fate of the wooden stronghold. The rise of powerful, centralized nation-states like France under Louis XIV or Spain under the Habsburgs fundamentally altered the purpose of fortifications. For these new absolutist monarchs, a castle was no longer just a practical tool for local defense. It was a potent symbol of state power, a permanent declaration of royal authority meant to awe subjects and intimidate rivals for centuries. Stone was the only material worthy of this message. Its sheer cost and the decades required for construction were features, not bugs. They demonstrated the immense, patient resources of a kingdom that could commit generations of wealth and labor to a single project. A wooden fortress, no matter how effective, could never project this image of eternal, unshakable power. It was too quick to build, too pragmatic, too associated with local lords and frontier communities. The state wanted monuments, and monuments are carved in stone. This cultural shift was embodied by a new school of military engineering, the Tres Italien or Star Fort. These were low, sprawling, geometric fortresses made of earth and brick, designed specifically to withstand and mount cannon. Their angled bastions eliminated defensive blind spots, creating overlapping fields of fire that made a direct assault suicidal. While these new forts often incorporated wood in their internal structures and palisades, their core was earth and masonry. They were incredibly expensive and could only be built by the direct order and treasury of a powerful central state. The age of the community-built gourd or the quickly erected palanka was over. Defense was now a national project, and its architecture reflected a new, centralized world order. But to declare wood entirely obsolete would be a grave historical error. Its utility never truly vanished. It simply retreated from the main stages of European power politics and found new life on the peripheries. In the vast wilderness of North America, throughout the 17th and 18th centuries, wooden stockades remained the primary fortification for both European colonists and indigenous nations. The French fur traders built a network of wooden forts throughout the Great Lakes and Mississippi Valley to protect their lucrative trade routes. The British erected wooden outposts along the frontier, and these structures proved their worth repeatedly in conflicts like the French and Indian War, where the rapid pace of warfare and the immense distances involved made stone construction utterly impractical. Even in Europe, insurgent groups and rebellious populations, lacking the resources of a state, returned to the old ways. During the great peasant revolts in Germany or the Cossack uprisings in Ukraine, rebels would often throw up traditional wooden fortifications as strongholds, using the same timeless principles of timber and earth that their ancestors had relied upon. They were building for survival, not for prestige, and for that, wood was still the undisputed champion. This enduring practicality reminds us that technological change is never a simple story of the new replacing the old. It is a tangled dance between capability, culture, and cost, where the best solution is always the one that most intelligently answers the specific needs of its time and place. Yet even as the great wooden fortresses of the world began to fade from the landscape, their core principles of speed, adaptability, and modular construction found a new and aggressive purpose, not in defense, but in the relentless grind of offensive siege warfare. Imagine the scene: a massive stone castle, its defenders smug behind walls that have withstood every assault, confident that a long siege will eventually see the attacking army wither from disease and starvation. But then, on the surrounding hills, a new silhouette begins to rise with shocking speed. Within days, a smaller, wooden counterpart to the besieged castle takes shape, its own towers staring down the defenders. This was the siege castle, an offensive weapon built from the most defensive of materials, and it turned the entire psychology of a siege on its head. These were not crude field fortifications. They were prefabricated instruments of psychological and tactical domination. The genius lay in their assembly. An attacking army on the move would carry with it, in its vast baggage train, pre-cut timber components, standardized beams, pre-assembled ladder sections, wall panels, and even parts for multi-story watchtowers. These were the IKEA flat packs of medieval warfare, designed for rapid assembly under the most stressful conditions imaginable. Upon arriving at a target, specialized engineering corps, often called ingeniators, would direct the construction. Soldiers, acting as a coordinated labor force, would slot these components together, knowing that every hour spent exposed was an hour under fire from the castle's archers. The speed was not just convenient, it was a matter of survival, and it allowed a besieging force to transform a vulnerable field camp into a fortified offensive base in a matter of days, not months. The design of these temporary strongholds was a masterclass in applying pressure. They weren't meant to be beautiful or permanent, they were meant to be functional and intimidating. The most common and effective form was the counter-castle. Built on high ground directly overlooking the besieged fortress, Its primary purpose was to serve as an elevated artillery platform and observation post. From its wooden towers, attackers could now look down into the enemy courtyard, spotting troop movements and vulnerable points. More importantly, they could mount their own siege engines, trebuchets and mangonels, at a height advantage, allowing them to pound the enemy walls with plunging fire that was far more accurate and destructive than anything launched from the ground below. Other siege castles took the form of a circumvallation, a continuous ring of wooden forts and connecting walls that completely encircled the target, cutting off all supply lines and escape routes, transforming the mighty castle from a fortress into a prison. Our most vivid accounts of these structures come from the chronicles of the Crusades, where European armies, operating far from home and unable to call upon local resources for stone, relied heavily on their mastery of wood. The siege of Jerusalem during the First Crusade stands as a legendary example. Facing the formidable walls of the Holy City, the Crusaders found themselves stymied, suffering heavy losses from sallies by the Fatimid defenders. Their solution was a breathtakingly ambitious building project. Using timber scavenged from the surrounding countryside and from ships they had dismantled at the port of Jaffa, they constructed two massive siege towers along with a series of smaller forts to protect their camps. These were not simple ladders on wheels, they were multi-storied wooden castles in their own right, armored with soaked animal hides to resist fire and packed with soldiers. The psychological impact of watching these monstrous wooden giants creep toward their walls, each level swarming with enemy knights, was a devastating blow to the defenders' morale, a key factor in the city's eventual fall. The ultimate irony of the siege castle is its near-total disappearance from the physical record. Built for a single, brutal purpose, they were abandoned and dismantled the moment the siege was over, their valuable timber reused for other projects or simply left to rot. They have left almost no archaeological trace, no foundations to study. Their existence is known to us almost entirely through the written word in the detailed chronicles of monks like Fulcher of Chartres, who described their construction with awe, and in the administrative records of kings, which meticulously account for the vast quantities of timber, nails, and carpenters' wages required to build them. This ephemeral nature makes them a ghost in the historical machine, a critical yet invisible component of medieval warfare that we can only reconstruct from texts and a logical understanding of military necessity. By embracing these temporary wooden marvels, we complete our understanding of wood's indispensable military role. It was not merely a material for passive defense, waiting patiently behind its walls for an attack. In the hands of a determined besieger, wood became an active, aggressive tool of conquest. It allowed an army to bring its own fortress with it, to literally build dominance on the enemy's doorstep, and to apply a stranglehold so complete that even the strongest stone walls could eventually be suffocated into submission. The siege castle was the ultimate expression of wood's versatility, proving that the same principles that made a gourd or a stockade so resilient could be inverted to create one of history's most effective instruments of offensive siegecraft. For centuries, the grand narrative of military architecture was written in stone, simply because stone was what remained. The mighty wooden fortresses that once defined entire landscapes had seemingly vanished, leaving behind only the faintest of ghosts, a subtle discoloration in the soil, a vague mound on a hilltop, a local legend whispered over generations. Their stories were consigned to the footnotes of history, dismissed as primitive precursors to the real castles of legend. But today, a technological revolution is sweeping across the field of archaeology, acting as a time machine that allows us to peer through the veil of earth and time to finally read the lost chapters written in wood. We are no longer limited to what we can see with the naked eye. We can now listen to the stories the very soil has been keeping secret. The most powerful of these new tools is LiDAR, which stands for light detection and ranging. Imagine being able to strip away an entire forest, every single leaf and branch, with the flick of a switch. LiDAR makes this possible. Mounted on aircraft, it fires millions of laser pulses at the ground, measuring the precise time it takes for each one to bounce back. By filtering out the returns from vegetation, archaeologists can create a breathtakingly detailed, bare earth digital model of the terrain below. This technology has become the great revelator, uncovering landscapes shaped by human hands that are completely invisible from the ground. In the dense woodlands of Poland, LiDAR scans recently revealed the perfect, ghostly circle of a previously unknown Viking ring fortress, a discovery that sent shockwaves through the historical community and forced a complete re-evaluation of the Vikings' reach into Eastern Europe. Similarly, in the jungles of Central America and the moors of Britain, LiDAR is exposing vast networks of ancient settlements and fortifications, proving that our ancestors shaped their world on a scale we are only just beginning to comprehend. But once a site is located, the real detective work begins, and it requires a painstaking millimeter-by-millimeter examination of the earth. The primary evidence for a wooden structure is almost always negative space, the shadow it left behind. The most telling clue is the post hole. When a massive timber rots in the ground, it leaves a distinct, often darker, patch of soil where the organic matter has decomposed. By meticulously mapping the pattern, depth, and diameter of these post holes, archaeologists can reconstruct the entire floor plan of a fortress. The size of the holes tells them the girth of the timbers used, the depth indicates the height of the wall, and the pattern reveals the sophisticated joinery techniques, such as whether the posts were set singly or in paired slots to hold horizontal beams. A scatter of charcoal might indicate a violent end in a fire, while the microscopic analysis of soil samples can reveal traces of the daub, the mix of clay, straw, and dung used to weather-proof the walls. Another silent witness is dendrochronology, or tree ring dating. When a preserved piece of timber is found, perhaps a waterlogged chunk from a moat or a charred beam from a hearth, scientists can analyze the pattern of its growth rings. Each ring represents a year, and the pattern of wide rings, good growing years, and narrow rings, drought or cold, is unique, like a barcode. By comparing this pattern to a master chronology that has been built for a region, they can pinpoint the exact year the tree was cut down. This doesn't just give us a date, it provides a vivid snapshot of history. We can learn that a fortress was built in a single season from trees felled the previous winter, or that a repaired section of wall used timber from a forest 50 miles away, telling a story of resource management and logistics. It transforms a ruin from a static object into a dynamic event with a precise beginning. The cumulative effect of these discoveries is a paradigm shift in our understanding of the past. We are learning that wooden fortresses were not rare outliers but were, in many times and places, the dominant form of defense. Their networks were more extensive, their designs more sophisticated, and their builders more numerous than the historical texts, written by and for the elites who built in stone, ever acknowledged. Each new post-hole map, each LiDAR image, is a quiet rebuke to the old narrative of linear progress from primitive wood to advanced stone. It reveals a parallel history of engineering excellence that was literally rooted in the landscape, a history we are only now, thanks to our own technology, able to recover and finally appreciate, giving voice to the countless builders whose genius was written not on parchment, but in the earth itself. What if the blueprint for the cities of tomorrow has been waiting for us in the ruins of the past? The same principles that allowed a Slavic Gord to withstand a Mongol battering ram, or a Japanese Yamashiro to dance through an earthquake are now being rediscovered by modern engineers, not as historical curiosities, but as urgent solutions for a world facing climate change and resource scarcity. This isn't about nostalgia, it's about recognizing that the ancient builders of wooden fortresses were masters of what we now call sustainable and resilient design. They understood something we are only now relearning, that true strength isn't about resisting nature with brute force, but about working with it through intelligent adaptation. Their legacy is resurfacing in some of the most exciting architectural innovations of our time, proving that the most advanced material technology might just be the one we've been using all along. At the forefront of this revival is a material that sounds like something from a science fiction novel but is deeply rooted in ancient wisdom: mass timber. The most prominent example is cross-laminated timber, or CLT. Imagine taking multiple layers of dimensional lumber, standard boards, and stacking them in alternating directions, then bonding them under immense pressure with structural adhesives. The result is a solid wood panel that can be massive in size, incredibly strong, and remarkably fire-resistant. The genius of this design echoes the composite structure of a Viking ring fortress wall. Just as those walls used interlocking timbers to distribute stress, the cross-graining in CLT prevents the wood from splitting under load, creating a monolithic panel that has the compressive strength of concrete and the tensile strength of steel, but at a fraction of the weight. This lightness is a game-changer for earthquake resistance, as a building made of CLT has less mass, meaning it experiences lower seismic forces during a tremor, allowing it to sway and absorb energy just like its Japanese wooden predecessors. This connection to ancient joinery is even more direct. Modern architects and engineers, particularly in seismic zones like Japan and New Zealand, are actively studying the Shinbashira central pillar system of old pagodas and castles. The goal is to translate that flexible, pivot-based damping into contemporary skyscrapers. We're now seeing designs for tall buildings that incorporate flexible timber frames and specialized damping systems that allow the entire structure to rock gently on its foundation during an earthquake, then settle perfectly back into place once the shaking stops. This stands in stark contrast to the rigid, brittle nature of concrete and steel frames, which can suffer catastrophic failure if pushed beyond their limits. The wooden fortress didn't fight force, it managed it, and that is precisely the philosophy guiding the next generation of resilient architecture. It's a shift from building armor-plated bunkers to creating structures that can bend like a reed in the wind, enduring precisely because they know how to yield. Beyond its structural brilliance, wood presents an unparalleled environmental advantage in an era defined by the carbon crisis. The production of our two most common modern building materials, concrete and steel, is devastatingly energy-intensive. The chemical process of making cement, the key ingredient in concrete, alone accounts for around 8% of global carbon dioxide emissions. Steel production requires burning vast quantities of coal in blast furnaces. A building made from these materials essentially has a massive carbon debt before anyone even moves in. Wood, however, operates on a completely different restorative cycle. As a tree grows, it does the opposite of emitting carbon. It absorbs it, pulling CO2 from the atmosphere and storing it securely within its fibers. When that tree is harvested and turned into a building product, that carbon remains locked away for the lifetime of the structure, which could be centuries. A single large mass timber building can sequester thousands of tons of carbon, effectively making it a carbon sink rather than a carbon source. Furthermore, sustainably managed forests ensure that for every tree harvested, new ones are planted, creating a perpetual, renewable cycle of material production that cleans our air instead of polluting it. The practical benefits extend to the construction site itself, showcasing a level of efficiency that would make the builders of a Viking ring fortress nod in approval. Mass timber components are typically prefabricated in a factory with computer-guided precision. These large panels and beams are then shipped to the construction site and assembled with astonishing speed, like a giant high-tech Lego set. This method drastically reduces construction time, noise, and waste compared to the messy, weather-dependent process of pouring concrete and welding steel. A project that might take 18 months with conventional methods can be structurally assembled in a matter of weeks using mass timber. This precision also leads to a much tighter, better insulated building envelope, significantly improving energy efficiency for the occupants over the long term. From the sustainable harvest of the raw material to the speed of assembly and the long-term energy savings, wood demonstrates a holistic resource efficiency that our current linear system of take, make, dispose simply cannot match. By embracing these lessons, we aren't just copying old techniques. We are synthesizing ancient wisdom with cutting-edge technology to create a new architectural language. This new paradigm allows us to envision future cities that are not only safer and more resilient in the face of natural disasters, but are also actively restorative to the planet. Imagine urban skylines where serene, biophilic towers made of wood rise against the sky, their very presence helping to mitigate climate change. These would be cities that breathe, whose buildings are not static monuments of consumption but dynamic participants in an ecological cycle. The wooden fortress teaches us that the highest form of engineering is not to dominate our environment, but to harmonize with it, to use our intelligence to create structures that are as kind to the planet as they are strong. This forgotten wisdom, carved in timber and tested by time, is now emerging as one of the most powerful tools we have to build a truly sustainable future. Perhaps the most persistent and damning myth is the idea that wooden fortresses were inherently primitive, a crude first draft before the supposedly superior age of stone. This perception paints them as temporary, flimsy structures, little more than glorified fences thrown up in a panic. The reality, unearthed by archaeology, couldn't be more different. These were not simple camps. They were sophisticated, multi-generational community centers designed with a level of foresight that rivals any stone castle. Take, for instance, the Slavic Gourds. Excavations reveal intricate networks of internal log-built houses, workshops, and even temples, all laid out with deliberate planning within the protective embrace of the walls. They weren't just for soldiers, they were thriving towns, complete with advanced infrastructure. Archaeologists have found evidence of complex drainage systems designed to channel rainwater and waste away from living quarters, preventing flooding and disease, a feature many later medieval stone castles sorely lacked. Some sites even show signs of rudimentary underfloor heating, using channels for warm air to circulate, a luxury that speaks to a deep understanding of comfort and engineering. The very fact that sites like Biskupin show evidence of being occupied, maintained, and expanded over hundreds of years completely shatters the notion of their temporary nature. These were permanent settlements, the hearts of their communities, built to last and designed for a quality of life that went far beyond mere survival. Then there's the myth of fire, the seemingly obvious Achilles heel that has been used to dismiss wooden fortifications for centuries. It's a simplistic assumption that ignores the brilliant, multi-layered defense strategies employed by their builders. Yes, wood burns, but these engineers were not naive. They were brilliant pragmatists who developed a whole arsenal of countermeasures. The first line of defense was material selection. Builders frequently used dense green timber, freshly cut wood still saturated with sap and moisture. Try lighting a campfire with a wet log. It's an exercise in frustration, producing more hissing steam than flame. A fire arrow striking a wall built from such timber would often fizzle out on impact, leaving little more than a blackened scar. Beyond that, they applied physical and chemical barriers. Thick coatings of clay, mud, or lime-based whitewash were standard, creating a fire-resistant crust that shielded the flammable wood beneath from direct contact with flames. In many cases, this daub was mixed with horsehair or straw for added strength, effectively turning the wall into a primitive but highly effective composite material. The architecture itself was also a form of firefighting. The deep earthworks backing the wooden walls acted as natural fire breaks, containing any blaze to a single, manageable section rather than allowing it to race along the entire perimeter. And of course, every fortress had dedicated fire watch teams, constantly patrolling with buckets of water, sand, and wet animal hides, ready to swarm any spark the moment it appeared. Fire was a managed risk, not an automatic death sentence. The persistence of these myths isn't an accident of history, it's a direct result of historical bias. The chroniclers of the medieval period were most often in the employ of kings and high nobles, the very patrons who were investing fortunes in building imposing stone castles as symbols of their eternal power and divine right to rule. Their job was to glorify these monumental projects, writing lavish accounts of the decades-long construction of a stone citadel served to magnify their patron's legacy. The humble wooden fortress, by contrast, was often the defense of the common folk, the smaller lord, or the frontier community. Its stories were recorded in local oral traditions or administrative ledgers that were far more likely to be lost to time, fire, or simple neglect. This created a historical record that was overwhelmingly skewed toward stone. When a wooden fortress did appear in these chronicles, it was often in the context of its destruction, reinforcing the false idea of its inherent vulnerability, while its many successful, unrecorded defenses were simply forgotten. The physical evidence compounded this bias. A ruined stone castle leaves an unmistakable skeleton of carved rock on the landscape for centuries. A wooden fortress, when abandoned, quietly returns to the earth, its timbers reused, rotted, or burned, leaving only subtle ghosts in the soil for archaeologists to later discover. We built our understanding of the past on the evidence that was easiest to see, and in doing so, we wrote the wooden fortress out of its rightful place in history. Dispelling these myths does more than just correct the historical record. It fundamentally changes how we view the intelligence and resourcefulness of our ancestors. It restores credit to the countless anonymous carpenters, engineers, and community leaders who looked at the forest around them and saw not a limitation but an opportunity. They didn't have the limitless resources of a king. They had ingenuity, a deep understanding of their material, and a pressing need to protect their homes. Their solutions were not primitive. They were elegantly adapted to their environment, their threats, and their means. By acknowledging this, we move from a simplistic narrative of technological progress, where newer and harder materials are always better, to a more nuanced appreciation of appropriate technology. The wooden fortress teaches us that the most brilliant design isn't always the most monumental or permanent. Sometimes it's the most resilient, the most adaptable, and the most intelligent use of the resources at hand. It's a lesson in humility and brilliance that continues to resonate, challenging us to see the past not as a linear march toward superiority, but as a rich tapestry of diverse and ingenious solutions to the universal human need for security and community. It's one of the most fascinating questions in the history of technology. How do you get the same brilliant idea in nearly identical form, popping up in places that had absolutely no contact with each other? When we look at a Slavic Gord in Poland, a Viking ring fortress in Denmark, and a Japanese Yamashiro, the similarities are so striking they can feel uncanny. These cultures were separated by thousands of miles of land and sea, with no means of communication, no shared blueprints, and no trade in architectural ideas. Yet they all arrived at a nearly identical conclusion for how to build the perfect defensive stronghold. They built in circles, they fused wood with earth, and they mastered the art of the flexible joint. This isn't a coincidence. It's one of history's most powerful examples of convergent evolution in engineering, where the same environmental and military pressures acting on intelligent human minds produced nearly identical solutions time and time again. The circular layout is perhaps the most visually obvious of these shared features. From the perfect rings of Trelleborg to the concentric rings of a Celtic hill fort, the circle was the shape of strategic choice. Why? Because the circle is the most defensively efficient shape possible. It eliminates the weak, vulnerable corners that plague square or rectangular forts, those deadly blind spots where attackers could gather somewhat sheltered from defensive fire. A circular wall ensures that every single point on the perimeter is visible from another point on that same perimeter, allowing for overlapping fields of fire. An archer in one tower can cover the approach to the wall for the archer in the next tower, creating a continuous, deadly curtain of arrows that leaves no safe approach for an enemy. It's a geometric solution to a universal military problem, and cultures from Scandinavia to Japan independently discovered that the circle was the answer. Then there is the universal principle of composite construction, the fusion of wood and earth. Whether it was the Slavic builder packing soil behind his interlocked timber cribs, the Viking engineer filling his Laftewerk framework with stone and rubble, or the Japanese architect raising his plaster-coated walls on a massive earthen base, they all understood one fundamental truth. Wood alone could flex, but it could be broken. Earth alone was strong, but it could be eroded. But combine them, you create a miracle material. The earth provides the immense, immovable mass that absorbs and deadens the kinetic energy of a projectile. The wood provides the flexible, tensile strength that holds that earth in place and prevents it from washing away. Together, they create a defensive matrix that is greater than the sum of its parts, resilient to impact, resistant to weather, and incredibly difficult to breach. This wasn't a secret passed from one master builder to another. It was a logical conclusion anyone would reach after watching how different materials behaved under stress. It was applied physics discovered independently on multiple continents. The third great convergence was in the hidden language of joinery. While the specific techniques had different names, the block bow of the Slavs, the intricate Laftewerk of the Vikings, the shin-zukuri of the Japanese, the underlying principle was identical: build to move. They all understood that a rigid structure is a brittle structure, so they designed connections that allowed their buildings to breathe, sway, and settle. They used joints that transferred weight and stress through friction and interlocking geometry, not just rigid fasteners. They preferred wooden pegs that would swell with moisture, tightening their grip over time, over iron nails that would rust and loosen. This universal understanding that a fortress should be a dynamic, living entity, not a static monument, is perhaps the most profound shared insight of all. It reveals a deep, intuitive grasp of material science that allowed them to turn a perceived weakness, flexibility, into their greatest defensive strength. So what forces drove this remarkable convergence? The answer lies in facing common, terrifying enemies. For the Slavs and the Vikings, the primary threat was the lightning-fast cavalry charge of nomadic steppe warriors, the Avars, the Magyars, and later the Mongols. These armies relied on speed, mobility, and overwhelming shock tactics. A circular fortress with no blind spots and earth-backed walls that could absorb the impact of 1,000 charging horses was the perfect counter. For the Japanese, the relentless enemy was the earth itself, in the form of catastrophic earthquakes. Their need for flexible, swaying structures was a direct response to this existential threat. In both cases, the design was a perfect, logical adaptation to a specific, overwhelming pressure. The problem was different, but the engineering solution, flexibility through composite wooden construction, was essentially the same. This phenomenon is exactly what scholars like Jared Diamond explored in his work on the interconnectedness of human societies. He argued that while details differ, human innovation often follows predictable patterns because we are all solving similar problems with similar cognitive tools. The invention of agriculture, the development of writing, and the evolution of military technology often appear in parallel because the underlying needs to eat, to record, to defend are universal. The independent creation of the wooden fortress is a classic case study of this principle. It shows that when the survival of your community is at stake, the human mind is capable of extraordinary leaps of logic and creativity. And often, the most intelligent solution is so obvious that it will be discovered by anyone staring at the same problem with enough urgency and ingenuity. This global pattern doesn't diminish the achievement of any one culture, it elevates it. It tells us that brilliance isn't a rare fluke confined to one part of the world. It is a universal human trait waiting to be unlocked by necessity. Recognizing these shared threads weaves a richer, more connected tapestry of human history, one where we see ourselves not as isolated tribes with separate stories, but as a single, ingenious species, capable of reaching for the same stars, even when we can't see each other's fires burning in the night. History's grandest battles are often remembered for the generals and the empires, but some of the most profound tales of courage were written by ordinary people standing behind wooden walls, their names lost to time but their defiance echoing through the ages. These stories strip away the abstract notions of engineering and strategy, revealing the raw human spirit that gave these structures their true, unbreakable strength. Consider the siege of the small Rus Principality of Kozulsk in the spring of 1238. The Mongol war machine, the most formidable military force the world had ever seen, had already crushed the armies of much larger and wealthier cities. Their arrival at Kozulsk, a minor town defended by a wooden Kremlin, should have been a mere formality, a footnote in the relentless Mongol advance. But the people of Kozulsk, from the prince's son to the lowest farmer, looked upon the endless sea of horsemen and made a choice that would become legend. They chose to fight. For 7 interminable weeks, this humble wooden fortress became the immovable object to the Mongols' unstoppable force. The chronicles describe a nightmare of attrition for the besiegers. Mongol catapults, which had reduced stone towers to rubble, hurled their massive stones at the timber walls, but instead of shattering, the wood groaned and yielded, absorbing the impacts in great, splintered wounds. And each night, under the cover of darkness, the defenders would perform their miracle of repair. Using pre-prepared beams and earth-filled baskets, they would swarm the damaged sections, their work illuminated only by the enemy's distant campfires. By dawn, the wall would be whole again, a sight that must have chipped away at the morale of the most disciplined Mongol warrior. The fortress's design allowed for this, but it was the sheer, stubborn will of the people inside that made it happen. They weren't just patching wood, they were defying the inevitable, their hammers and saws sounding a relentless drumbeat of resistance. When the Mongols finally breached the walls after this grueling campaign, the cost had been astronomically high in time, resources, and men. In a fit of frustrated rage, the Mongol commanders reportedly dubbed it the Evil City, a backhanded tribute to the unbelievable tenacity of its defenders. The fortress fell, but its story did not. It became a beacon, a proof that even against absolute overwhelming force, a determined people, empowered by a resilient stronghold, could make conquest unbearably costly. Centuries later and an ocean away, a similar drama of defiance unfolded in the smoky blue hills of Tennessee. Fort Loudoun, a British outpost built in Cherokee territory, found itself besieged not by a foreign horde, but by its former allies, the Cherokee Nation. Relations had soured, broken promises had led to bloodshed, and by 1760, the Cherokee warriors had the small wooden stockade completely surrounded, cutting off its supply lines and subjecting it to constant harassment. Inside, the British garrison and their families faced starvation and despair, yet they held on month after grueling month. Their survival was a testament to the dual strength of their wooden fort and their own ingenuity. The stockade's design, a classic example of frontier adaptation, featured a double wall of logs packed with earth, which effectively absorbed musket balls and even small cannon fire from the Cherokee, who had acquired their own artillery. But the key to their prolonged resistance was a secret weapon the plans could never show, a hidden subterranean water source. A cleverly concealed tunnel had been dug from within the fort's walls down to the nearby riverbank, allowing the besieged defenders to sneak out under cover of darkness to fetch water, a lifeline that kept them alive long after the Cherokee believed they had them throttled. This act of clandestine endurance highlights a critical point. The best-designed fortress amplifies the cleverness of its defenders. The Cherokee, masters of woodland warfare themselves, were being confounded by a technology that mirrored their own practical wisdom. The siege became a tense game of cat and mouse, a psychological battle as much as a physical one. The British, though eventually forced to surrender when their food truly ran out, had demonstrated the incredible staying power of a wooden fortification. Their prolonged stand, fueled by that secret water supply, forced the Cherokee to commit significant resources and time to the siege, altering their own strategic calculations and ultimately leading to a negotiated outcome rather than a simple massacre. The story of Fort Loudoun isn't one of ultimate victory in the classic sense, but rather one of profound resilience. It shows how a well-built wooden fortress could serve as a potent equalizer, allowing a small, isolated group to exert an influence on events far beyond what their numbers should have allowed, bending the arc of conflict through sheer, stubborn endurance. These narratives, from the frozen banks of a Rouge River to the humid American frontier, converge on a single, powerful truth. The timber, the earthworks, the clever joinery, these were merely instruments. The true heart of the fortress, its ultimate source of strength, always beat within the people it sheltered. The engineering provided the opportunity for courage to manifest, for communities to bond under pressure, and for the human spirit to find a way to resist. A stone castle is a monument to the power of the Lord who built it. A wooden fortress is a testament to the will of the people who defended it. The wood itself was a partner in this struggle, a material that allowed for adaptation and repair, reflecting the very flexibility and resilience of the human character. These stories remind us that in the long sweep of history, the most formidable defense is never just a wall, but the unwavering resolve of those standing behind it. Yet this journey through time is far more than an academic exercise in correcting the historical record. It feels almost prophetic, as if these ancient builders left behind a blueprint not just for defending a hilltop, but for navigating the profound global challenges we face today. The core principles that made a Slavic Gourd or a Japanese Yamashiro so resilient: adaptability, sustainability, and a deep harmony with local environments are precisely the same principles we are desperately seeking to embrace in our modern world. Confronted by the escalating climate crisis and the alarming depletion of finite resources, the monolithic, energy-intensive approach of 20th century construction, reliant on concrete and steel, is increasingly revealed as a dead end. We are now being forced to reconsider everything we thought we knew about strength and permanence, and in doing so, we are turning back to the wisdom embedded in timber and earth, discovering that the path to a resilient future might just be paved with the lessons of a forgotten past. This isn't merely a philosophical shift, it's a practical revolution taking place in architecture firms and engineering labs across the globe. Historians specializing in medieval technology are now collaborating directly with structural engineers, creating a fascinating new field of study. They are using advanced computer modeling to simulate the dynamic forces that a Viking ring fortress wall would have endured, not to write a paper, but to inform the design of modern earthquake-resistant buildings. The ancient Shinbashira central pillar system of Japanese castles, which allowed the structure to sway gracefully during a tremor, is being directly studied and adapted for use in modern skyscrapers made from massed timber. These tall wooden buildings are designed to flex and dissipate seismic energy rather than fight it, a direct application of a 700-year-old insight that is suddenly cutting-edge technology. It's a stunning collaboration across centuries where dendrochronologists and software programmers work side by side, proving that innovation isn't always about inventing something new sometimes. It's about remembering something brilliant we chose to forget. The environmental imperative behind this revival is even more compelling. The production of concrete and steel is one of the largest contributors to global greenhouse gas emissions, a brutally unsustainable process that our planet can no longer afford. Wood, by beautiful and stark contrast, is the only major building material that is truly renewable. A sustainably managed forest doesn't just provide timber, it actively cleans our atmosphere, with trees absorbing carbon dioxide throughout their lives. When that wood is harvested and used in a building, that carbon remains locked away for the entire lifespan of the structure, which could be centuries. This transforms a wooden building from a passive object into an active carbon sink. Imagine entire city districts constructed from mass timber, their very presence helping to mitigate climate change rather than accelerate it. This is the powerful, restorative potential we are unlocking by looking backward, embracing a material that aligns with ecological cycles instead of brutally interrupting them. Beyond the science and engineering, this reevaluation carries a profound cultural and ethical weight. For centuries, the history of architecture and engineering has been written with an overwhelming Eurocentric bias, celebrating the stone monuments of kings and empires while systematically ignoring the ingenious wooden achievements of Slavic, Scandinavian, Native American, African, and Japanese builders. By finally acknowledging the sophistication and global prevalence of wooden fortress engineering, we are doing more than just adding a few new entries to the history books. We are engaging in a vital act of historical restitution, giving voice and credit to the countless cultures and anonymous builders whose contributions were erased by the bias of chroniclers who valued monumentality over practicality. This corrects a deep injustice, weaving a richer, more inclusive, and far more accurate tapestry of human ingenuity. It teaches us that brilliance is not the sole property of any one culture or era, but a universal human trait that flourishes wherever there is a need to protect what is most valued. Ultimately, this isn't about nostalgia for a simpler time. It is about arming ourselves with a broader, deeper toolkit for survival. The wooden fortress teaches us that resilience is not found in unyielding rigidity. but in the capacity to adapt, to repair, and to work in concert with our environment. Its story is a powerful antidote to the hubris that we have nothing to learn from the past. As we stare down a future of uncertain climates and scarce resources, the most progressive thing we can do may be to look back to those who mastered the art of building strong with simplicity, who understood that true security comes not from dominating nature, but from learning its rhythms and harnessing its intelligence. Their legacy offers us a vision not of retreat, but of sophisticated, sustainable advancement, a way to build a world that is not only stronger, but wiser and more harmonious for all. From the mist-shrouded gords of Slavic tribes to the earthquake-defying Yamashiro of Japan, these wooden fortresses stand as powerful testaments to a form of strength that has nothing to do with brute hardness. For centuries, we've been taught that permanence and power are carved in stone, that the only legacies worth remembering are the ones meant to last 1,000 years. But this journey through the forgotten chapters of engineering history reveals a more profound, more human truth. True resilience isn't about being unbreakable. It's about the capacity to adapt, to bend without shattering, and to heal your own wounds even in the midst of the storm. These builders looked at the forest around them and saw not a limitation, but a partner. They understood that intelligence could forge a more dynamic kind of strength from flexibility and ingenuity than from any amount of rigid, unyielding rock. We've walked the ramparts of these wooden marvels and seen how they defied not only sieges but the very biases of history itself. They were not primitive precursors to stone castles. They were parallel and often superior, innovations born from necessity and a deep understanding of local materials. They shaped the destinies of cultures, from the Slavic communities who found sanctuary from steppe nomads to the Japanese clans whose swaying castles became the hearts of their domains. Their practical solutions, the shock-absorbing composite walls, the fire-resistant treatments, the modular repairs were not just effective for their time. They are a reservoir of wisdom that is startlingly relevant today, offering blueprints for sustainable building and disaster-resistant design in an era desperately searching for answers. As we reflect on these overlooked wonders, let it be a reminder that history's most valuable lessons are often hidden in plain sight, waiting for us to look past the grand monuments and listen to the whispers of the earth. The story of the wooden fortress is a call to reevaluate what we think we know, to challenge the narratives handed down to us, and to find inspiration in the ingenious solutions of the past. If this exploration into history's resilient wooden hearts has sparked your curiosity, we'd love to hear your thoughts in the comments below. Share which fortress amazed you the most, or what forgotten marvel you think we should explore next. For more journeys into the overlooked corners of our world, make sure to subscribe and hit the bell so you don't miss our next adventure. Together, let's keep unearthing the stories that reshape our understanding of the world, one hidden wonder at a time.